Hello, everyone. Good afternoon, good evening. Welcome to TensorFlow Everywhere SSA. Today, we'll be covering a number of topics, a number of presentations. We have a packed schedule. We want to value your time, so we're going to get started immediately. As with all events, whether virtual or they're in person, we do expect that everyone please follow community guidelines. Be respectful to each other. In the comment section, you can ask questions, but also make sure that you don't harass anyone, you don't post any profanity. Just be good to each other. We're going to have a very good time exploring what's new in TensorFlow and a lot of other amazing topics. Our first speaker, Robert John, will be joining us in a few seconds, and he'll be taking the first talk. So I'm going to invite Robert John right now to the screen, and also ask him to do a brief introduction and welcome everyone to his talk. Robert, over to you.
Thanks, Anyedi. Hi, everyone. My name is Robert John, and I am a Google developer expert for machine learning and the Google Cloud Platform. Welcome to TensorFlow Everywhere, Sub-Saharan Africa. And my talk is going to be on what's new since TensorFlow 2.2. So I'll just share my screen and get started. Okay, so I'll be talking about what's new in TensorFlow, and specifically this is targeted at version 2.4, but you can still access these features in experimental even if you don't have version 2.4. These features are typically divided into two categories. The first category is focused on model building, and the second category is focused on performance optimization, basically speeding up your models once you're done. So, sorry. So on the model building, we've got NumPy. Specifically, it's called tf.experimental.numpy. And what this does is it lets you utilize NumPy from inside of TensorFlow. It's not the same thing as using NumPy directly, because we know NumPy traditionally only runs on the CPU. But tf.experimental.numpy will let you work with NumPy from other devices, GPUs and TPUs. On the model building, we also have Keras preprocessing layers. And finally, we have a TF recommendation library called TF Recommenders. And on the performance improvements, we have new features in tf.data, as well as improvements to the TensorFlow profiler. Unfortunately, we won't be able to cover all of these topics, so we'll try and cover the first two, which is experimental NumPy and preprocessing layers. Okay, so first off with tf.experimental.numpy, the goal here is for you to be able to accelerate your NumPy. Now, NumPy is something that if you learn machine learning from scratch, if you have to learn the algorithms, linear regression, logistic regression, you tend to start off with something like NumPy, especially if you're working with Python. So we all know that NumPy only runs off of the CPU. That's the primary constraint, but it's pretty straightforward. It's an awesome numerical computation library. And there's no reason why you can't keep using it as long as it serves your purpose. So now what we have with tf.experimental.numpy is that it works with TensorFlow. So you can run a subset of NumPy on various devices now using experimental TensorFlow. And these devices are CPUs, which is traditional, or GPUs, if you've got GPUs on your machine, or even TPUs if you're running in the cloud. So in addition to improving performance, TensorFlow Experimental NumPy offers interoperation with all of TensorFlow's APIs. So what this means is you can backpropagate through NumPy code with tf.gradient tape, which is awesome because tf.gradient tape itself was an awesome provision that helped with your your calculus for computing loss, right? You also have the ability to use NumPy code with APIs like tf.data and tf.keras. Again, that's awesome. You're able to distribute NumPy code with tf.distribute and lots of other things. Essentially, you can mix and match your NumPy code with all of TensorFlow. So here's an example of some code that we have. If you're not running TensorFlow 2.4, then you can use TF nightly. But if you're using TensorFlow 2.0, then 2.4, then it's available to you to use, right? So all you have to do is import TensorFlow.experimental.numpy. And while we typically subset NumPy as NP, in this case, we're going to subset experimental NumPy as TNP, right? And so what you have is you can see that you can go ahead and you can create a random normal distribution using tnp.random.randn, and you can go ahead and clip it. And now what you have on the line that follows next is where you print x.data.device. And what it does is it tells you what device it's carrying out that operation on. So if you've got a GPU, it will tell you that it's running off of the GPU. And that's the example output that you have on the screen. Now, you're able to go ahead and plot this. The ND arrays that you create using tnp.random.randomnormal are wrapped around tensors. So previously, what you would have is that you would need to go from a NumPy array to a TensorFlow tensor and back, and you would have to do a bunch of transformations. This time around, you don't have to do that. So the ND arrays are wrapped around tensors, but they're still compatible with other libraries that expect NumPy arrays. So if you're working with something that expects a NumPy array, it will work just fine. And if you're working with something that is TensorFlow compatible, then it will still go ahead and work just fine. Now, you can demonstrate this by passing this array that we made into matplotlib. So matplotlib expects a NumPy array and ND array. And so what you see in the code is we import matplotlib.pyplot, and then we can go ahead and plot. And the interoperability works since ND arrays implement the correct NumPy array interfaces. So you don't have any problem there. The code just works, nothing breaks, right? Now, you might be wondering, okay, so we know that this isn't actually NumPy. This is something else, but just how fast is it? And on the screen, what we have is we have a performance example, and it's available on the tensorflow.org website as well. Now, what you see is the blue line here shows the traditional performance from NumPy. Okay, so NumPy that only runs on the CPU, this is the performance here. Now, the next line here, which is the orange line, shows the performance improvement once you just implement your NumPy on TensorFlow. So NumPy TensorFlow on CPU, without even bringing in a GPU, has a performance improvement. And that's what you see with this orange line. The next line, which is the green line, makes use of something which is called compiled TF NumPy. And you're going to see that in subsequent slides. And finally, you've got TF NumPy running on a GPU. So this just shows you the kind of performance improvements that you can expect with the same operation as you go from your traditional NumPy through various implementations of TF NumPy. Okay, so on the screen now, what we're going to do is we're going to make use of TensorFlow NumPy and then create a tf.data, the data set. And so you have that implementation on the screen. And the only difference here is that instead of using your traditional NumPy, you're using TensorFlow NumPy. Okay, moving forward, you can go ahead and compute a gradient. Okay, so this kind of looks similar to what you would be doing with your traditional NumPy, where you'd be multiplying your inputs with your weights. Now, at this point, we're making use of TensorFlow gradient tape, right? So we're now able to compute gradients. Previously, with NumPy, you'd have to do something else, but here, you're able to use gradient tape. But note here that you have to use tape.watch. And the reason why I'm using tape.watch is that these weights, they're not tf.variable, right? Instead, they're TensorFlow NumPy. So you have to watch them. But once you do that, you can go ahead and carry out your matrix multiplication. And in this step, we even go ahead and compute a sigmoid for it, right? And then you can return your gradient. And optionally, you could also choose to use a batch Jacobian if that's what you want to use. It's also supported. Now, moving forward, you can write code with your traditional Python control flow. So you can use your Python loops to iterate over the input pipeline and compute gradients for different input batches. Okay, so just think of this like stochastic gradient descent. So you can use these gradients later on to train a model. So what you see on the screen is that TensorFlow NumPy is NumPy, but it also works natively with TensorFlow. Now, moving forward, you can introduce a few things. So notice that previously we manually computed our sigmoid. Now, the challenge with machine learning is that it's not just knowing the algorithm or the equation that counts, but there's also a need for optimization. So in this case, what we make use of here is the TensorFlow.math.sigmoid function. And what we're doing here is we're interleaving with TensorFlow APIs. Now, because it's native, NumPy API calls can be freely interleaved with other TensorFlow APIs, right? And the tf.math.sigmoid that we're using here is better optimized, and it's also said to be more numerically stable than the handwritten version that we just used in the previous slides. So we're able to do this. Our code still works perfectly well. Now, we also change our code to compute per example gradients. And what this does is it computes gradients for each element of the input batch, right? And this is done by using TensorFlow's map function API to map the gradient function over each element in the batch. Okay. You can typically get more information about this from the TensorFlow.org website on dealing with TensorFlow NumPy. Okay, so moving forward, at this point, what we then see is that further down, we introduce something, and that's the TF function, right? So we take advantage of TensorFlow's compilation and vectorization. And so that is, it gives us that line that we saw in the performance graph that we looked at earlier. There was a line somewhere between TF NumPy and TF NumPy on CPU and TF NumPy on GPU, and that was called TF NumPy compile. So this is the actual compilation step. Okay, so we have compilation and vectorization here. So putting a TF.function decorator traces and compiles the function to create a highly optimized version which gets invoked on future calls. Okay, so it's an advanced thing, but if we switch our TF.map function to TF.vectorized map, it will trigger auto vectorization to speed up and fuse the computation. Now, it's a bit complicated, but you can read about it on the TensorFlow.org website. So these optimizations speed things up. If you look carefully, you can see that these optimizations can speed up your code on a GPU by a factor of up to 100 or even more sometimes. And so you can see it here in this performance graph. And notice that this is not a linear scale. This is actually a logarithmic scale. So these steps here, this is not 10, 20, 30, 40. This is actually 10, 100, sorry, this is 1, 10, 100, and 1000, right? So it's powers. And so those are the optimizations that we get. And so this blue is just the performance that we had when we wrote the first version of the code, which is just iterative. The orange here is the performance that we got when we introduced compilation. And then there's this green down here, which you might not even notice, but this is the performance we get when we make use of both compilation and vectorization simultaneously. Okay, so to summarize, not all of the features are supported, so it's just a subset of the features. But in the future, you can expect to see certain things, such as in-place mutation of ND arrays, support for more ops, fast operation dispatch using TensorFlow runtime, lower level APIs for distribution, and key NumPy library support. So examples of those will be tracks and scikit-learn. It'll be awesome to see scikit-learn support in TensorFlow actually, so fingers crossed for that. Okay, so moving on quickly, I'll just cover Keras preprocessing layers. And what preprocessing layers are is that they solve a very peculiar problem. And the problem that they solve is that while you have a model, it's important to remember that models are strictly numerical, right? So what happens when you're dealing with something that is not numerical? What happens when you're dealing with images, when you're dealing with videos, when you're dealing with text data? So you need to perform something called preprocessing. In the case of dealing with text, if you're building a text classification model, for instance, then you know that you need to do some things. You need to carry out conversions on your text. You need to convert the text to lowercase. You need to remove punctuation marks and special characters. You need to split sentences into words or tokens, and then you need to convert all of those into their numerical representations, right? So there's all of that you have to do. And you have to do that for your training, but you also have to repeat the same thing during inference time. So you essentially have to duplicate code. And we all know that the one thing you don't want to do in writing code is duplicating code, because what it means is every time you change something in one place, you have to go off and change something in the other place. So now preprocessing is able to live within the model instead of living outside of the model. So with Keras preprocessing layers, what you have is a user-friendly way to build your model. You can include your preprocessing logic as a layer, one or more layers inside of your model. So depending on what you're doing, if you're dealing with images, you're able to do things like random flip, for example. You're dealing with text, you're able to carry out the tokenization, for example, or the standardization. So what One other advantage that you get with this is that if you're able to put the pre-processing as a layer inside of your model, then you'll be able to take advantage of any device that that model is running on. So if the model is running on the GPU, then you will leverage that GPU to carry out all of your pre-processing. So let's take a quick look at this. We're looking at an example of a text model, right? So in this case, we're going to introduce text vectorization as a pre-processing layer. So what you do here is you create a layer which is called text vectorization. And if you're used to working with language models, then some of these parameters will make sense. So max tokens make sense. Output sequence length also makes sense. And so what you need to do here is adapt it to your vocabulary, which again makes sense, right? To work with language models, you need to have a certain vocabulary that you're working with. So you adapt that layer to the vocabulary. And once you do that, the next thing that you do is you go ahead and you create your typical Keras model. So what we have here is a TF that Keras is sequential, and every other thing should look familiar. So layers that are embedding makes sense. Dropout, global average, pooling, dropout things, right? The first layer that we have is the vectorized layer. And with that, you're able to do whatever you want to do. You can go ahead and train the model. You can save the model and load it up later on and do whatever it is that you want to do. So these pre-processing layers, they have support for a number of things. They have support for text. So with text, you can standardize, tokenize, and vectorize. They have support for images. You can resize, normalize, and run data augmentation on the GPU if you have a GPU. And there's also support for structured data. So for numeric and categorical attributes, one-hot encoding, hashing, discretization, bucketization, and lots of things. These are things that existed with TensorFlow estimators. You were able to, there were some strong libraries for those, but with Keras, you had to do a bunch of things to make it happen. But luckily, we have those here now. So you can learn more from the TensorFlow.org website. Developer guide and complete examples are available. You can also check out Keras.io for some documentation, especially for the pre-processing layers. You can use either Keras.io or TensorFlow.org. So with this, I will stop the presentation here and take a few questions because we're almost out of time.
Thanks, Robert. We've got a few questions. Let me find one here. So we have a question from Tim's Owen. Will gradient tape differ if I'm performing derivatives from a function and change it later? Will its performance be tampered? Does it allow manual change?
So I must say I'm not sure, frankly, because I think the problem might be I do not fully understand the question. Yeah, so I will just confess that the answer is I don't know. Will performance change later? Well, of course, it depends, because one of the things that I didn't mention is that sometimes you even have data being copied, especially if you're moving between devices. So sometimes if you're doing something, there's a data copy, and a data copy has a performance implication. So it's something that you need to bear in mind. But what I should say is you should definitely take a look at in the documentation on TensorFlow.org website. it states some critical differences between what you should expect with the traditional NumPy versus TensorFlow experimental NumPy. So if you bear those in mind, then you will understand where, for instance, with the function that you mentioned, if you change the function and if it's changing something, maybe what exactly it is that your ND array is interacting with, or the device on which the operation is going to take place, then you can expect a potential slight performance hit. But again, if what you're doing is moving from CPU to GPU, then in the end, you're still going to have a performance optimization.
Awesome. So maybe I'll ask one question my own. So with all the things you've mentioned about what's new with TensorFlow 2.4, what's the one thing that really stands out for you, or probably something you may have already started using or you're planning to use or change in the sort of like your workflow?
So that's a really good one. And I will say that NumPy really stands out. Although I think, yeah, it really stands out for teaching, particularly because when you're teaching and you need people to understand the theory, what you typically start with is traditional NumPy before you introduce TensorFlow. And then there's usually all of the headache about, hey, but with NumPy, all we had to do was use td.readcsv to load up our data, and then we were working with NumPy. But with TensorFlow, you have a bit of acrobatics. And then you're explaining that, well, actually, by the time you get to TensorFlow, you're dealing with massive amounts of data, and that people need to understand that what TensorFlow is doing is that it's laying a foundation that makes it possible for you, once you're done with all of the booting up and everything, that you just take off like a rocket, right? So with TensorFlow NumPy, you now have some of those advantages of TensorFlow coming into the NumPy ecosystem, meaning that you can have a sort of smoother transition for people coming from the classroom examples of toy data sets and NumPy, and now saying, okay, let's work with a much larger data set, right? So for instance, if you go from the Titanic data set, which is how many hundred examples, and you jump to the New York taxi cab example, which is millions of rows of data, you're then able to say, okay, here's how you leverage a bunch of things. So here's how you leverage your back propagation or your gradient tape. So yeah, it's one thing that has really stood out for me. I would say secondly, though, is that pre-processing layers are awesome in production. So you might not use them a lot in teaching, but in production, they are just wonderful.
Cool. Okay, we've got a question from Kennedy Njoroge, and it's on the screen. How different is text vectorization from tf.keras.preprocessing the text tokenizer? Does it replace it?
No. So what tokenization is really is just saying extract word tokens. So in English, we don't have so much of a problem with tokenization in the sense that most words are themselves tokens, unless you have them in like a present continuous form, right? So traveling, the actual token and the root word is travel. And he travels, she travels, I traveled, I will be traveling. The token there is travel. But there are other languages that I'm aware of, and German is one example, and I think Japanese and Chinese also have that, where what looks to us like a word is actually a sentence. And so tokenization breaks that very complex thing down into the individual tokens. But vectorization is a numerical representation of the token. So you'll have tokenization before you have vectorization. So vectorization is not replacing tokenization.
Okay, and then our last question will be from Nuruddin Sambo, and it says, Is there any trade-off when using tf.numpy instead of the core NumPy library?
Well, not a performance trade-off, but recall that we said that currently only a subset of operations are implemented. So we will not replace it will not replace the traditional, the core NumPy library 100%. But then again, that also depends on the extent to which you use your core NumPy library. So frankly, for me, when I see the things that haven't been implemented, I really don't use them when I'm teaching. So I don't have that much of a problem. Okay, Anidi, so I think I'm done.
All right, thank you very much. Thank you very much, Robert. That was a very, quick run through of subsections of what's new with TensorFlow 2.4. We're going to move on to our next speaker. We're doing very well on time right now. So I'm going to invite John Quinn, and he's going to introduce himself, and then we'll go ahead with his section. Hello, John.
Hey, Nidhi, how's it going? I'm John Quinn. I'm excited to be here and speak to people in Ivory Coast. After all this time in Ghana, we've not really had much interaction across the border, so it's great to be here with everyone.
So awesome. I think you would be best in the best position to introduce yourself. So I'm going to jump off the screen, allow you to introduce yourself, and then you can share your screen with your presentation.
Thanks very much. Sounds great. Yeah, so I'm John. I'm a senior software engineer in Google's research office in Accra, where we started up around, let's see, 2018. I guess we're a year or two in now. I've been working in African applications of artificial intelligence for a while. So I worked in Uganda for about the last 10 years. And to me, this is really fascinating, what we can do with AI in this context. So I'm hoping to give you a bit of an idea of some of the things going on in Accra just now, things we're interested in, particularly to do with the satellite imagery and mapping. So I think we're good to go. I'm not too familiar with this platform. I hope my slides are showing. Thanks, great. All right, so I want to discuss some work. So this is a few people in Accra. We have some collaborators also in Zurich, a number of us involved in this. And the idea is to do better at mapping buildings from satellite imagery. So as you look at Google Maps, you may notice that some areas have more complete information than others. And there's various information online about how the buildings get into maps. I think there's been a few blog posts on the way that satellite imagery is used, computer vision pipelines to take the images and try to work out where roads are and where buildings are and put them on the maps. And it works better in some places than in others. So, for example, if you look in parts of Cape Town here, you can see that many of these buildings aren't making it onto maps. So that's quite an important issue. If we want these things to work equally well for everyone, and then also being able to know where buildings are is important for lots of stuff. For national statistics, for planning. There's all kinds of reasons why this is something that we would want to be able to do better. So why is this difficult? If you really look at large areas like a whole country or the whole continent, there's really this big range of different types of buildings. When you go from Cairo to Lagos to Abidjan, I mean, there's all sorts of types of structures and types of geographies that we have to deal with. So that makes it quite challenging, especially where we have these very small things very close to each other, then for image segmentation algorithms that can pose a challenge. So what we've been doing is working on a model based on UNet. So UNet is often used for image segmentation, and there's two parts to it, an encoder and a decoder. And the encoder's job is to take the pixels in the image and come up with some kind of representation, some low-dimensional representation of what's happening inside that image. And then the decoder outputs whatever we're interested in, which in this case is like the positions of buildings. We try to label each pixel as, is there a building at this position, yes or no? And then after that, we try to find which are the separate buildings. We kind of cluster out the individual structures. So what we've been doing in our team over much of last year was taking a baseline model and improving it bit by bit. And I'll kind of run through a few of the things we did, which seem to help. Some tips, if you have a task like this, is to start off with the evaluation measure, even before you really have a model that starts to work. If you have a test data set and some way of measuring a metric that we can use to evaluate, then you can start like trying different things bit by bit and gradually increase it. So what we looked at was mean average precision. So to get this balance between like how many false positives are we getting and false negatives. And you can see over the months, we kind of gradually increased this. So part of this was like architectural things, like trying modifications to the model, retrain, see if it works better, like different loss functions, data augmentation, pre-training, stuff like that. So, you know, over time, you try each of these things in all sorts of different combinations, and you know, gradually this gets better. So how does this look now? Here's an example of one of our best performing models. So we have some imagery here, and you can kind of see in the pixels that there's you know, some buildings in there. The UNet gives us this segmentation, so we can see like these are logits from the model, so you can see like pixel-wise where buildings are and where they're not. And to get this last stage where we find the individual buildings, all we do is super simple at this stage. We threshold at some confidence level, and then we just say, well, which are the groups of pixels which are kind of connected together after that. So here's another example of one of these quite challenging from a computer vision perspective. One of these examples where you have lots of small structures close together, and this is one of the things that UNet seems to handle quite well. Deserts are quite difficult as well, more challenging on the vision side, because you have buildings which appear very similar to the surrounding area. You know, I guess ideally for this kind of segmentation, you would have some contrast between the thing you're trying to detect and the background regions around it, and that's not always the case, but we can still do okay there. So, you know, long story short, we are putting this in the pipeline so that we can take a satellite image and then pull out buildings that we then get polygons from, and then we can add these to the maps front end, so the Google Maps works better. So what's next? I'll wrap this up here so we have a bunch of time for Q&A and to discuss whatever people are interested in. But what's happening next? So we're looking at trying to improve the front end to make maps better. So we've already identified quite a number of new buildings and added them on, and we're starting to work on road detection. You know, I'm sure many of you have seen that, like, sometimes you know, roads are missing, or there's extra roads which aren't really roads, and you know, it could be with that same kind of process we could do a bit better at modeling and follow this same kind of procedure. Another thing a bit longer term is we're interested in, like, what are the other implications of being able to detect buildings better? You know, could there be things we can do in like national statistics or humanitarian applications, working with the partners who need this kind of data, maybe there are interesting things to do there. So we're exploring in that direction as well. Okay, so I'm going to stop talking there, and I'd love to hear what questions you have, or anything we can discuss which is interesting. Thanks very much.
Really very interesting, because that was really very practical. I'm going to pop into the chat very quickly to see if there are any questions. But like I said, one of the things that people are always very excited about is understanding a little bit more about your background and your journey. So if you want to tell us just a little bit about some of the things, that brought you to where you are, and some recommended resources, we'll be very, very excited to hear about that.
Yeah, thanks. Thanks, Anyedi. So I guess particularly in terms of like artificial intelligence in Africa, maybe this is like an interesting thing, because this is really taking off now. Like 10 years ago, it was there wasn't so much activity, and I think with now there's so many open source resources, and connectivity is better, that kind of thing. So for me personally, my early part of my research career was in medical machine learning. So I worked in like monitoring in intensive care units. I moved to Uganda in 2007 to join Makerere University in the computer science department. And at the time, wasn't really thinking too much about like what machine learning opportunities there might be in that kind of context. But then it turns out there's all sorts of things. So, medical applications, agricultural, you name it, there's all sorts of challenges. Predicting road congestion. We've worked on things like monitoring environmental things. So there's a number of applications which are interesting there. So resources, you'd asked about what kind of things can people get into. There's a couple of groups going on which are pretty interesting. I've been involved pretty closely with Data Science Africa over the last sort of 5 years or so that we've been running it. I know there's some other interesting groups going on as well. I think these are pretty exciting places to be. So that's a little summary. I think maybe we lost Anyedi there. Okay, while performing data augmentation, does the repeat function affect model if I run out of training epoch? Well, I think if you're training, you want to set the number of epochs to be unlimited, right? Like, because if you're augmenting, then maybe you don't necessarily just have to do one epoch of the data and stop there. You can run through it as many times as you like, because you're augmenting and it's never exactly the same data. I'm not too sure specifically about the behavior of the repeat function. So I'm not too sure about the behavior of that. Great, thanks for the question. What would be the best resources for remote sensing and satellite imaging? So I think there's been some really nice competitions recently. So let me just type some things in. So like SpaceNet 7 is a competition that happened last year. It was a NeurIPS competition, and with that there was a lot of data and benchmark source code. So there's kind of a starting point there. There's not much like really in one place. So remote sensing and deep learning are like a little bit fragmented fields. So it's not quite like doing ImageNet, where there's lots of prepackaged resources that the information might be in different places. There was also another competition, CVPR Deep Globe, and they had 3 different tracks in this competition. One was building detection, another was roads detection, and another was land cover classification. So like for every point in the image, is this cropland, is it built up, is it is it road or is it water, for example. That can be a nice starting point, because in the competitions, again, you've got the data and so on, and you can also see what people did and whether it worked. So that might be one way to begin. Cool. Applications of machine learning in agriculture. Any word of advice? So I guess there's different things that can be done with agriculture. One of the things which I worked on previously in machine learning and agriculture in Uganda was in diagnosis of viruses affecting plants from the image. Can you take a photo with a phone and then run some classifier to be able to say this is this disease or that disease. There's lots of other things too. So agriculture is a big area. There's the way that people trade, for example. I think there's some interesting work in like the way the markets work, like connecting buyers and sellers. It's maybe less kind of deep learning, but there's interesting like resource allocation problems there, which are quite computational. There is like a remote sensing angle as well. So forecasting the yield of crops is pretty interesting, I think. Like if you can look at climatic connections, she's having trouble with, we know the feeling, I feel the pain. Yeah, so like satellite imagery can be pretty interesting for agriculture as well. Like has it been wet or dry? You can use these images, which are basically like how much rain has fallen and how green was the vegetation index. A couple of things like that. If you have any elaboration, I'd be happy to kind of drill in deeper. Like if there's a particular sort of aspect you're most interested in, like diagnosing diseases or yield prediction or any of these other types of applications. Okay, let me answer this one, and then maybe we'll hear more about agriculture. Open problems around satellite imagery space. These are great questions. Thanks, everyone. Okay, so to me, some of the interesting things. Okay, so people are working, including us, on like building detection and road detection. There's lots of other things on the Earth's surface which might be interesting. And I think if you look at what happened in deep learning for photographic images, one thing with the data sets is they have everything labeled. You have like a cup sitting on a table, and there's a plate and a knife and a fork and a chair and a cat. And everything in the whole scene is labeled. So that seems pretty interesting. Like I don't really think there's much like that which exists for satellite imagery. Another thing about satellite imagery, which is kind of cool, is that every pixel has a location on the Earth's surface. So you know exactly where it is spatially and what time it was taken. So you can actually combine images from many different satellites together. And I think that's pretty interesting, because you can't do that with photographs. You can never know exactly where the pixel of, where exactly that was in space. So there's loads of satellites. I mean, all of us are having satellites flying over our heads all day. So, there's various like public data sources, Landsat, Sentinel. Then there's also this like higher resolution imagery that you find, for example, in SpaceNet datasets. And I think like joining them together is a kind of ongoing field of work that seems pretty interesting. Soil image data. So I don't know too much about this, but there are things there are data products which are already computed that you can use to input into other models. One of them is soil moisture content. And maybe I'll try to, I'm not very good at multitasking, but I'll see if I can search for this and put a link in. Yeah, you can download data which is like, you get the area you're interested in. Maybe it's maybe it's like the district you're in or something, and you have like a grid, and they're often quite large grid cells, like a kilometer or something, and it would say like how much soil moisture is there. Another thing is vegetation index. So like it's not quite the soil or the vegetation, but it's quite easy to download that, which is effectively a measure of like kind of how green. It takes the green and near infrared bands and looks at how strong that is, so you can track like growing seasons and climatic conditions. Although that's about the vegetation, so it's not quite what you asked about soil. Yeah, I don't know too much more about soil, I'm afraid. Okay, I see a question on the chat here. Is it possible to work with satellite imagery on flood and traffic for my community? Yeah, great question. Traffic is more difficult. So one of the downsides of satellite imagery is you only get the image whenever the satellite happens to be flying above. So the most frequent ones, like Sentinel, is open free data, and it flies over approximately once every week. You get an image, but then the pixels are like 10 meters across. Like one pixel in the image is a 10-meter square on the ground, and if there was any clouds above, then you can't see anything. So it's maybe not so good for traffic, because traffic you need to know like here and now. It's no help to know what traffic was like a week ago or the last time there was no clouds. Flooding though is pretty interesting, because maybe that timescale is okay. And I think that's a really interesting area of work, like training classifiers which take, for example, Sentinel data, and trying to classify each pixel in that image, which is a 10 by 10 meter square on the ground, and saying like, is this water or not? And then you can look at like new areas which are water since last week, and so then you could like monitor the extent of floods. Any resources? Okay, let me do some quick search there while the next. Oh, thanks, Abdullah. Yes, CVPR Deep Globe. I think I put that in the chat. I'm not sure if I'll see if I can put the link in. Okay, I hope that I hope you can see that link and I'm typing it into the right place. deepglib.org, right? Okay. All right. I guess we're done with the questions. Nidhi, are you back? Thanks, Robert.
Okay, thank you very much, John. Unfortunately, Anita is having connectivity issues, which is why he's been going on and off, and he's trying to sort that out in a few minutes. So I'll just take over from him until he can get back on stage. But thank you once again for taking our time to attend to all the questions, even with all the mishaps that we had to that happened. So yeah, I'll be taking you off stage. I'm sure you can go on to the chat section on the YouTube live stream if other people have other questions for you, or maybe you can share your preferable social media contacts that anyone can reach out to you if they have more questions, or basically any way they can reach out to you if they have more questions.
Sure, sounds good. Thanks so much. I'll keep an eye out for the questions on the chat, and it was really great hearing all your questions and ideas. Look forward to interacting more.
Thank you very much. All right. So moving on to the next person. Hi everyone, my name is Adam Katwiyum, and I've been backstage helping out with every other thing. Like I mentioned, Anyidi will be picking up from where he stopped in a few minutes, depending on when he can fix his internet connectivity. We already know how it is with connection issues here in SSA. But in the next few minutes, I'll be calling up our next speaker, which is Derek Mwiti. Derek will be, so I'm going to add you to stage now, Derek. Hi, Derek.
Hi.
Great. Hi, welcome.
Thank you.
All right, so Derek will be speaking on training and deploying machine learning models on edge devices. So would you like to give a very brief intro about yourself, what you do before you jump right into your session for today?
Sure. My name is Derek Mwiti. I'm a data scientist, and most of what I do involves building machine learning models and bringing them to production. So today we'll be talking about how we can actually deploy them on mobile devices. Of course, deploying them on the web is quite straightforward, but more and more interest is coming on the side of edge devices such as mobile phones, Raspberry Pi, Arduino, and so on. And so there's a special way to go about this, and not just the way we do it when we are building them for the web.
Okay, that's great, sir. I'm looking forward to your session. But just a quick reminder to everyone, while the different sessions are going on, please feel free to continue conversation on social media using the hashtags that are showing on your screen right now, which is hashtag TF Everywhere 2021 and hashtag SSA, so that other people can be aware of what's currently happening and possibly join and learn alongside you. So I'm moving the stage to you now, Derek. Over to you.
Thank you so much. I can share my screen. Okay, so as I was mentioning before, when building these applications for the mobile devices, we need a different, we don't use the normal TensorFlow, we use what is known as TensorFlow Lite. And this is just a framework that has been built for deploying machine learning models on mobile devices, as well as embedded systems such as Arduino and the Raspberry Pi and so on. So as I mentioned before, these models have been used for example, for text, that is doing classification, prediction. They've also been used for speech, and we know by now everyone is using this, the text to speech, the speech to text, as well as object detection. But there is also a new application that is coming up that is in audio and also generating of content. So in this session, what we'll discuss is how you can build a machine learning application, how we can use pre-trained models, and how you can train your models using Cloud AutoML, as well as how you can train models, TensorFlow Lite models using Keras and TensorFlow. Let's take an example of this image classifier. So how would you go about building this simple application? So the first thing would be to get a pre-trained model. So before you decide to train your own models, it's good to check if there are models that already exist that you can just borrow from, because the models are open source. And so one of the places you can get them is the TensorFlow Hub. And this is simply like a GitHub for open source machine learning models. On this platform, you will find both TensorFlow Lite models as well as normal TensorFlow models. And these are pre-trained, so you can just start using them right away. There are so many models you can get on the TensorFlow Hub. And so before you start building your own models, for example, if you're doing something for image classification, you need to collect the images, and training these models could take a lot of time. So the first thing you'd actually want to do is to check whether there is a model that you can use. Furthermore, even if your problem is a bit different, you can still use a pre-trained model and just change it a bit using what we call transfer learning. And this will make the process of building your machine learning model faster. So when you go there, you can check on one of the models that you like to use and then select it. So now, assuming you're doing this on Android, what you need to do first is to add the TensorFlow Lite dependencies to your module build.gradle file so that you can be able to access the functionality. Now, let's take an example where you've downloaded the MobileNet mobile application. Where you've downloaded the MobileNet TensorFlow model. Now, after you download this, what you want to do is to put it in your assets folder of your application. And so this is the way you would load it into your application. So now, once you load it, you will need to create a new interpreter. And you create a new interpreter you can create it using these default interpreter options. And after that, you can run the model. And also to note that depending on the way the model was built, you might need to say do things such as resizing your images, just to make sure that the images are in the way that is expected by the model. You'll also need to load in the labels. So for example, the MobileNet model contains like 1,000 labels. So you need to load in that too. And so you can store your model and the labels in the assets folder. And then you will be able to load them using the TensorFlow Lite support module. So now, assuming you've been able to load them, the next thing will be to now get your predictions. Now, when getting your predictions, you'll get them in a quantized form. This is just means that these models there are some operations which have been applied to these models just to make them smaller for mobile devices. So what you need to do is to adjust them and so that you can get the probability. Now, in this case, for example, when you get this probability, you can set a threshold of, say, 50%. And then now, since you already have those labels, you'll map that to the labels, and then you'll be able to get the label for that specific image. Once you get the label, you can do now whatever you wanted with it. In this case, it's just being displayed on a text view. There is also another way of importing your models in Android Studio, and that way is by using the Android Studio model plugin binding. Now, if you have the latest Android Studio, you do not need to do anything. So what you will do is just go to File, New, Other, and then you select TensorFlow Lite model. This will give you the option to select that TensorFlow Lite model. So now once you select it, it's going to be loaded into your application, and you also get some sample code that you can use. So for example, in this case, you get your Kotlin code as well as your Java code. And so anytime you want to go back to that code, that sample code, you just need to click on on this location on your Android Studio application. Apart from using pre-trained models, you can also use the Google Machine Learning SDK for mobile applications, and that is MLKit. The advantage of using MLKit is that you don't need any machine learning experience. These are just APIs that you can start using right away without any experience in machine learning. So for example, as you can see in these applications, you can use them for detecting the language of text. You can use them to decode a barcode, to detect faces, as well as to read text from images. These applications, the code for these applications are also available on my GitHub. So if you want to see the full application code, you can just check it on my GitHub profile. So let's assume that now you want to build a mobile application that you're going to host on, say, Google Play Store. And we know that the process of making updates for your applications on Play Store might take some time. So let's say, for example, you ship your first version of your application, and then let's say that you change the model. So now, in that case, they would mean that you also need to ship another version of your application. But now, if you use a Firebase to host this model, you will not need to ship another version, because the only thing you'll need to do is to just change the version on Firebase, and the version will reflect in your application. Let's take a look at how this can be done. So you need to go to Firebase, and then you create a new project. And then under machine learning, what you will do is create a new model, assuming now you already have your model, and then you'll give it a name. So in this case, it's being called MobileNet. So you need to master the name you give it, because you will need that when you go to write the code. So now once you've created the model, you've uploaded it to Firebase, the next thing you will do in your application is that you'll set the parameters for loading this model. Remember that most people are using these on mobile devices. So you want to ensure that in this case, you require that the user is using Wi-Fi before the model can be downloaded. And now, when using a model like this, now the challenge becomes, will the user wait for the model to download so that they can see the expected result? And so the way you go about this is you ship your application with a model that is going to be used before the online model is downloaded. And so in this case, you can see this code is familiar to what we've seen previously. So what you do is that you check if the model is downloaded, And if it is not, what you do, you just use the model that is available on the device. But now when the model downloads, the new model downloads on the device, what you want to do is to now change the model that is being used from the local one to the one now that has already been downloaded. And so in this case, the user will always be able to see the functionality you would like them to see. But then you can also, you'll also be using Firebase to manage your machine learning model. And so the advantage for that is that when you ship a new version of this model, you do not need to ship another version of your application. You can just change this on your on Firebase, where you are storing this model, and your users will be able to access it. Now, if the next thing you can do is to train your model with Cloud AutoML, and also the advantage of this one is that you also do not need a lot of machine learning experience. The only thing you need to be able to do is to prepare your data, and then you'll just upload it to the AutoML vision on Google Cloud. It's going to do the training for you, and you'll be able to get access to a model that you can use for your applications. At the moment, it supports a use of supports image classification as well as object detection. Another tool you can use to build your TensorFlow Lite models without much experience in machine learning is TensorFlow Lite Model Maker. As you can see in this case, the only thing you will need to do is to use the image. For example, if you're doing image classification, you use the image classifier data loader, then use .from folder. Then you'll pass in the folder where your images are located, and then you just split it, and then you'll create your model. After you create it, you can evaluate it and then export the TensorFlow Lite model. So you can see this is pretty straightforward and very easy. Even without any machine learning experience, you can use TensorFlow Lite Model Maker to create your TensorFlow Lite models. The advantage of using this TensorFlow Lite Model Maker is that you can even switch between architectures. Like, for example, the various architectures like ResNet, Inception. It allows you to switch between these architectures, and you can see that the process of building the models is quite easy. Alternatively, if you're very familiar with Keras and TensorFlow, you can build your own machine learning model from scratch. Once you do that, you can use TensorFlow Lite Converter to convert this model into TensorFlow or Lite version. So you'll just do the normal process of building your model, and then once you're done, you just convert it. You convert it to TensorFlow Lite. So in this session, we've seen that if you want to add TensorFlow to your mobile applications, even without any experience in machine learning, you can do it very quickly using a pre-trained model. You can train one using AutoML vision on the cloud. You can also use TensorFlow Model Maker to create your own models. And if you're familiar with Keras and TensorFlow, you can build a model and then convert it to TensorFlow Lite version using TensorFlow Lite Converter. So that's it, and then I guess you can take some questions.
Thank you very much, Derek. We have a couple of questions on the chat that I'll be popping up on the screen and then reading up as well. But there's some questions, there's some requests from the listeners. They're asking for the link to your GitHub profile so that we can possibly work on this. But one question on here is from Hakan. Sorry if I'm not pronouncing this well, but he's asking, can you explain why the model cannot be included with the app instead of having to be downloaded the first time?
I believe this is a question referring to the part where I talked about Firebase machine learning. And so what I was saying is that if you're going to ship you know, models are not built once. You keep you keep improving them. And so now the first time you build this model, it's very possible that you'll need to change this model as you keep improving. So what you're saying is that you can ship the model with your application. That is so that if someone before the model is downloaded from the internet, they will use the one that is on the device. However, the advantage for storing these on Firebase is that if your model is on Firebase, it means that when you make an update to the model, then you do not need to ship a new version of your application.
Okay. Thank you very much. So there are no more questions. And yes, Anidi is back temporarily. So I will just pivot back to the background and have Anidi back on stage. But thank you so much, Derek. Just quickly, can you drop or share the preferable social media handle that people can reach out to you if they have more questions because of time?
It's that one on the last slide that I was showing at _Mweti Derek.
Okay. All right. Thank you again, and over to you, Anidi.
Derek, I have one question for you. I hope my connection is good enough to take this question. You recently became a Google developer expert for machine learning. Can you just share a little bit about that journey and what this is like and how someone can become a Google developer expert for machine learning from your point of view?
Well, I thank you for that question. So from my point of view, I think the goal is not to become a Google developer expert, because that's not something I was even thinking about. So for me, I just saw it online and applied because I saw that what was required for a Google developer expert is something that I was already doing. So for example, giving talks, writing about machine learning and sharing content. So if you're someone who is passionate about sharing content about TensorFlow or about any Google product, then you'd be a good fit for the program.
All right. Thank you very much. It's been a pleasure having you and sort of introducing you to the community. If I'm not mistaken, this is one of the first talks we've had you since you became a Google developer expert. So I see I'm being given a couple of jabs because of my internet connection. Well, this is a classic problem in Africa, which is one of the reasons why Derek has just given us a fantastic talk about building machine learning models on edge devices and low resource devices. So there's a question on the screen here. Any trade-off between model development language, Python, and the app's native language, which could be Java or Kotlin?
Sorry, I didn't understand that one.
On the screen, he says, are there any trade-off between the model's development language, which usually is in Python, and the app's native language, which is Java or Kotlin? So I think most people have built their app in Java or Kotlin, and then when they first go to code, maybe build their model, they build that in following TensorFlow and Python, and then they convert it. So I guess the question is, when you do that sort of conversion to TensorFlow Lite, so you can deploy it on a device that is, or on an app that was built with Java or Kotlin, are there any trade-offs? Anything gets lost in translation?
Okay, so maybe the easiest way to explain this is that the way you get a TensorFlow Lite model is actually from a TensorFlow model. And so without getting too technical, you know that the way data is represented using float and using integers. So what TensorFlow Lite model is doing is just reducing the representation of that the data in order to make the model smaller. So in this process, a little bit of accuracy might be lost, just a little bit of it, but it's worth it because you get a smaller model with closer to the same accuracy. And so you can see someone asking about using a RESTful API. That is something that you can definitely do. But if let's just take an example, you've built a model for farmers somewhere in a rural place in Africa where they can use the mobile application to detect diseases in, say, their plants. And the connection there is not good. So you can see that your application will not be usable because they cannot access proper internet. And so the reason why we are saying we ship the mobile applications with, we ship the model with our mobile applications is because the user will always be able to access the functionality of your application, irrespective of whether there is an internet connection or not. However, if you're using the RESTful API, as you could, it means then that the user always needs to have an internet connection.
Okay. So there's a question from one of our organizing team members internally, and he's asking, why do you prefer to use TensorFlow Lite instead of deploying the model as a RESTful API?
I believe I've already answered that one just like a second ago. I was saying that if you're shipping this, just like you are saying, you can see that there are some connectivity issues in SSA. So if your application relies on internet, it means then that the person in a rural place, if that is the person you're targeting, it means then they will not be able to use your application because it requires internet. That is one thing. Number two, there is latency. If the model requires it to query from online or from a database somewhere, it means then your application is not as fast. So there is the issue of latency. So if it's on the mobile device, users are able to access the functionality quicker compared to accessing it via RESTful API.
Okay, so the last question that we'll be taking for your session before wrapping up is still from Hakan, and he's asking, are there any performance considerations when using quantized models as opposed to non-quantized distant models?
Yes. When you quantize a model, it means then that the data is represented in a different data type. Is it something called I forget the actual data type, but for example, if you're using float data representations, a floating number in computers can be a very long number. And so it means then that when you reduce this representation, you're losing a bit on the accuracy. And so it's a trade-off between getting a slightly less accurate model, but one that is small enough for a mobile device. So it's a game of balancing between reducing the size of your model and not losing on the accuracy part.
Okay, thank you very much, Derek. We're a little bit behind schedule, so we'll just wrap up your session now. And just like you mentioned, any of the viewers who would want to reach out to you for any questions can do so via the Twitter handle that's showing on the screen right now. So thank you once again, Derek, and enjoy the rest of your day.
Thank you.
All right, so moving on, we're going to take a very quick break, but in between that break, just to keep you glued to your screen, we're going to be bringing on someone very, very important who just his name is Olayinka Peter, and he just took the TensorFlow Developer Certificate. So we're bringing him up on stage to share more about the certificate and what the exam involved, and basically just for you to ask questions or to know the process behind this and to get insights from him as well. Hi, Olayinka.
Hi. Can you hear me? Hi.
Yes, can hear you. How are you doing? And thank you for
Very
joining
fine,
us.
thank you.
Hi, Anidi. Welcome.
Yeah, thank you very much. Can you hear me at all?
Yes, we can
Yes,
hear
I can hear
you.
you.
Okay, awesome. Ada, thank you very much for stepping in. So, Arinka, quick questions. First of all, just introduce yourself. I think that would be very useful for everyone.
Okay, hi guys. How's it going? My name is Arinka Peter Olafemi. I recently sort of like just passed the TensorFlow certificate examination. And I mean, it turned out that I was sort of like the first in Sub-Saharan Africa to sort of like get that certificate. So I currently work as a software engineer with Tangerine Life. I also work as an ML instructor at Sub-Saharan Africa. So, yeah.
Okay, cool. So, straight up, what would you say are the benefits of taking the exam?
Okay, I mean, amazing question. So I think that first off, the actual benefits of taking the exam come from sort of like when you're preparing. So usually your advice is sort of like prepare with the deep learning.ai Coursera, specialization, the TensorFlow in practice specialization. So whilst you're sort of like taking that particular course, I mean, it's sort of like really compact, packs a lot of use cases of machine learning itself, and then you're sort of like implementing these use cases with TensorFlow. So from computer vision, which includes image classification and stuff, to NLP, to time series prediction and sequences. Yeah, you sort of like learn. I mean, a lot of these things, and then you sort of like, in that particular course, there's a lot of practice, there's a lot of practices, the same way Coursera specializations are. And, this particular exposure and this particular, learning process sort of like gives you confidence in terms of, tackling TensorFlow problems, or rather tackling, machine learning problems with TensorFlow. So I think that that's first benefit for me, the fact that I was able to become more confident, and then I think another benefit is sort of like the community recognition. Yeah, so you get so feel like announce the certificate, and then you get, companies and HR sort of like reach out to you for opportunities and stuff. I recall that a number of LinkedIn messages came in, and a few persons reached out to me on Twitter as well. And the same benefits of like go across the other people I know that have taken the exam and have passed. So, I mean, the learning process, the benefits that come from sharing that particular certificate, and then people getting to reach out to you and stuff. Yeah, I think that's the benefits.
Okay. My next question I was going to ask you, someone has already asked. So congratulations. My question is the cost of the certification. Wondering if it's free.
Okay, so no, it's not free. So I think that the cost is $100. If I'm sorry, correct. So usually when I'm tense, I sweat. I'm sorry, forget sweat. So I was saying that the cost is $100. And what else? Yeah. So it's not free, but then you can apply for. Yeah, you can sort of apply for a. I think it's a fund support, and then they sort of like remove 50%. So instead of paying $100, you pay $50, and so you sort of like apply for that, that support, and then they will review that application, and if they find it, worthy of, worthy of that particular fund reduction, they'll definitely approve it, and yeah, you get to pay $50 instead of $100. So.
Okay, that's great. And then one more question from me. How did you prepare for the exam? So you've said a little thing about the deep learning.ai. Was that the only resource you used? Did you need to consult other resources? Before that, how much experience did you have with machine learning and TensorFlow before you took the exam?
Yes, I think that yeah, so of course, yeah, like so before preparing, you're sort of like supposed to be quite vast with Python. and then of course understand the basics of TensorFlow, and then you're supposed to, because you're still going to be writing the exam in PyCharm. So once you've picked, and then there's a validation process, you get to sort of like install the plugin. So there's a TensorFlow exam plugin. You install that plugin, and then you write the exam. The exam is 5 hours. Okay, I'm supposed to tell you the number of questions because you're supposed to sign something and say, hey, you're not going to tell someone outside the exam, Yeah, but then preparing is I think the most profound way to prepare for that particular exam is taking the deep learning AI specialization on Coursera. So yeah, once you've gone through that particular Coursera course, you are certainly about 70% ready for the exam, and of course, given that you sort of like went thorough on the course, of course, I mean, you finished all of the assignments, you know all of the different topics, so like you're well grounded in that particular course. I feel that particular course is enough, 70% enough to equip you for the exam itself. I remember sort of like running those models and praying that, because each of the models has a particular score. Your model, each model you build is supposed to, classify or predict with some certain past score, and so on one of that particular question or one problem they're trying to solve, I remember trying to pray and say, hey, go, yeah, so it's quite, yeah, well, it was really interesting. I mean, I was really excited that I was able to get pass mark, but then of course if you prepare adequately, you definitely try it once and then you definitely pass. So yeah.
Okay. So someone has a follow-up question. It's, do you do Android to be specific or just ML in general? So when you're taking the exam, do you go to like, oh, I'm a TensorFlow Lite person or I'm a TensorFlow.js person? Does it look much broader?
Okay, I think that I think I'm very, 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 very peculiar about machine learning, and I love TensorFlow to be candid, because I think that with TensorFlow, you get to be able to truly explore every branch of machine learning, and you get to be exposed, or I mean, you sort of like have a leverage to a lot of tools, a lot of pre-trained models, a lot of, I mean, TensorFlow.js, for instance, allows you to run machine learning on the web. Yeah, I mean, on client side, which is pretty amazing, and I think that's like one of the reasons why I really love TensorFlow. Yeah, and when it comes to specialization in terms of software engineering, I like to think of myself as a software engineer, not peculiar to one particular technology, but then I jump on technology because of passion. So yeah, I write Android quite well, and then I write Python web apps as well quite well. But in these two different fields, or in these two different specializations, I tend to want to explore machine learning to ensure that I'm automating or I'm building intelligent apps and solving business problems with that with that expertise of machine learning and TensorFlow. So yeah.
Okay, so someone is on the path to becoming TensorFlow certified, doing a specialization on Coursera. Is that enough?
Okay, so currently I think we're just about 5. I mean, and I feel that was sort of like a challenge for me. So I mean, I want to sort of like take on the responsibility of encouraging people to want to try to get that certification, because sort of like across the entire world, there are about more than 1,000 persons from the whole world who are currently certified, and in Africa I think there are about 10 out of more than 1,000. So, and in Nigeria we're about four right now, or 5. If I mean, I don't know. I've not checked recently, but yes. Please, way to go. Please, amazing stuff. Okay, so do you have to do anything else? Just Okay, maybe do a bit of extra reading about how to prepare, or try to ensure that you're very you can pick a simple collab notebook and do stuff with TensorFlow. Yeah. But then ultimately the Coursera specialization is going to sort of like equip you the most. The Coursera specialization is like the most equipping factor for that particular exam. I think that's BSQ I can give you. Yeah. Oh yes. So you run all models on your laptop. You run every model on your laptop. So you definitely want to use a laptop that has a standard CPU to run TensorFlow models.
All right. Thank you very much, Olayinka. I think just hearing from your experience is really very important for everyone. A lot of people thinking about this certificate or thinking about getting certified, or at least having some sort of credential for TensorFlow, maybe like, can I spend the money? Is it worth it? Maybe I should even ask you that, because I know you changed job recently. You did the certificate that gave you a new job, and have you jackpot? Are you now any rubber salary?
Trust me, it's worth it. Right? Trust me, it's worth it. Trust me, it's worth it. I've got good, yeah. I mean, it's worth it. Yeah, I think I should just stop there. It's really worth it. Yeah.
All right. Thank you very much for sharing. A couple of questions people have asked. As Olayinka mentioned, there's some aspects of non-disclosure. You have to just prepare yourself and then go and write the exam. You're not here to come and get expo. You're actually here for inspiration. So thank you very much, Olayinka. This was a real pleasure having you. So we're going to be taking a 20-minute break. So in about 15 to 20 minutes, we'll be coming back online. This is enough time for everyone to sort of like stretch your legs. It's time for me to check my internet connection and try and go and buy an internet connection and come back, since the 3 connections I have are not working. Interestingly, a lot of our speakers are based, some of our speakers are based in the US. So right now it is 6 a.m., 7 a.m., some places 8 a.m. So at the top of the hour, we'll be having our next session, which incidentally is going to be our keynote and our ML 0 to Hero sessions from Lawrence Moroni. So I urge everyone to take out time, use a bathroom break, reset your connections, check your emails. We'll be back very soon. Have your questions waiting. And we really look forward to interacting more with you. Let's all go stretch our legs, and we'll be back in approximately 15 minutes. See you soon. All right, welcome everyone.
Hey, how are
We
you?
should be live now. Okay, right now we are live once again. Great, and excited to have Lawrence Baroni joining us right now. So Lawrence needs no introduction. So I'm just going to hand over to him, and he's going to lead us through keynotes and the famous ML0 to Hero. Welcome, Lawrence. Good morning, and over to you.
Good morning, and thank you so much, and everybody, welcome to this event. I'm delighted to be here. It's early morning here in Seattle, so I'm still waking up. I have my cup of coffee, but I'm excited to be at least able to speak with you all virtually. But I'm looking forward to someday that when this pandemic is over, that we can do an event in person and I can meet you all in person. So today I'm going to do two talks. My first one is going to be the keynote, the TensorFlow Everywhere keynote. And as we saw, we're also going to do a 0 to hero, and I have a demo that I'm warming up right now that we can go over to show how image classifiers and those kind of things work. All right, I'm going to switch to my slides. Perfect, thank you. So TensorFlow Everywhere, what is this? It's really, we wanted to have a series of global events led by the TensorFlow and Machine Learning communities from all over the world. But we wanted to be able to support these events by having Googlers drop in and be there to be able to answer your questions and stuff like that. Now, we generally run, as Google, we run what's called the TensorFlow Dev Summit every year, as well as a TensorFlow Global Roadshow. But of course, since the last time we did this, lots of things have changed. The pandemic, the resurfaced fight for racial justice going on around the world, and many of us are experiencing changing personal circumstances and a different way of working. So in times of uncertainty, one of the things at Google is that we really see if we can turn to technology and turn to technologies like machine learning to help. And we personally found comfort in knowing that we're an important infrastructure that has the ability to help others. And one of the driving forces that we've had as a company is to see how can we apply our technologies to help others in many different ways. And TensorFlow is no exception. And there's a few examples that we're showing here of where TensorFlow was used in medicine, in protecting the environment, and working with farmers, and all of these kind of things to see if we could help build a better world. And many people have been using Google Meet to do education, to do study, to do their work, and all those kind of things. And we've seen that, like since March of last year, the daily usage of Google Meet has grown by 30-fold, and we're hosting about 3 billion minutes of video meetings every day. And we realized that when doing that kind of thing, the software needs to be adaptable for changing bandwidth, for picture quality, and things like that. And that's one place where TensorFlow, in a little way, has been helping. And some of the growth that we've seen in TensorFlow has been phenomenal. 200 million plus downloads, and apparently in the summer of 2020 alone, we crossed over having 10 million a month. Our tutorials and our guide views are over 50 million views now. On our blog, we've reached over 8.5 million views, and YouTube is actually, I believe it has just touched 10 million. It was 9.7 million when we created this slide. And we've been working hard to try to democratize learning about AI, to make it openly accessible using MOOCs like Coursera and Udacity, and working through universities. And we've had over 800,000 learners on these various online courses. So we can see it's a very vibrant ecosystem. It's a huge community. We're really delighted to be a part of that community alongside you, and we're doing our best to help that community grow and the people in that community to succeed. So what's all the fuss about? Well, it's about TensorFlow itself. And we like to look at TensorFlow in many ways, and like this architecture diagram is my favorite way of like really describing what TensorFlow is. So we think about TensorFlow as a set of tools to help you not just build machine learning models, but also to deploy them. And on the left-hand side of the diagram here, we can see the stuff that we've been working on that helps you build them. So it's the APIs for managing your data, for designing your models, for distributing the training, for the tooling, for looking at your models to make sure that they're working correctly or to try and figure out what's going on with them. On the right-hand side of the diagram are the places where you can use your models. So cloud and on-premises to be able to deliver a model via TensorFlow serving, devices and embedded systems via TensorFlow Lite, and being able to not just run inference, but also do training in the browser with TensorFlow JS, as well as on the back end with a node server. And this is all kind of held together by, there's a number of different ways of saving a model, but we like to think of save model as the de facto way of doing this. And all of these are bound by that, as well as a repository, TensorFlow Hub, where you can publish your models, or for the better part, you can actually take advantage of models that other people have published. So not everybody has access to millions of images to be able to train an image classifier, but Google does, and other researchers do. And as a result, instead of the research being available only to them, the models that they create with that can be published in TensorFlow Hub and can be reused, or through something called transfer learning, you can take the best parts of that and reuse them in your own model. We've been on a pipeline of releases. TensorFlow 2.0 came out, and to me, TensorFlow 2.0 is what was triggered this explosion in growth, because we were able to open it up with eager execution, and we were able to offer the simple high-level API with Keras. So now, TensorFlow and creating machine learning models with TensorFlow became more Pythonic, became more natural to coders. And we believe that kind of opened the gates so that people who are coders like me, I'm not a PhD, I'm not a researcher, I'm a coder, were able to take advantage of the underlying power of this to be able to build models and to be able to tweak models and make them more state of the art, and to use them and then to deploy them in places like on the right hand side of the diagram I showed a moment ago. But we didn't stop there. We've been growing TensorFlow with 2.1, where we added support for TPUs, and I'll talk about that a little bit later. And then with 2.2 and 2.3 to really double down on performance. And that's not just for training, but also for inference, to really make TensorFlow work harder and faster for you. And one thing I'd like to call out in 2.3 is this one here, where the experimental Keras preprocessing for data preprocessing. That if you've ever written any machine learning code, you'll realize that a lot of the fuss is about the machine learning itself, about designing the model, about neural networks and things like CNNs and LSTMs. But if you're writing this much code, this much of it is the model. And the rest, much of that is really about data preprocessing, understanding your data, how to use the data, how to change your data so that it can be represented within a machine learning model. And as a result, we realized that maybe 80% of the code that you write for machine learning is that. How do we make that simpler? How do we build some of that into the model architecture? So when we talk about Keras preprocessing for preprocessing layers, that's really what we're talking about. It's to see how much of this we can build into the model to make it more portable. And then we released TensorFlow 2.4 recently. And there's a few things in here that we've been working on, but I'd like to call out two of them in particular. The first one here are the improvements to distributed training. So think about when you're training a model, it requires a lot of power. You've probably heard about needing a GPU to be able to train machine learning models, and not everybody has access to a GPU, and we understand that. So we've released something called Colab that gives you access to a GPU in the cloud. But when your models get even bigger and even more sophisticated, training on a single device, a single GPU or a single TPU may not be enough. And you need to be able to distribute your training across multiple ones. So we call this distribution strategy. And being able to distribute your training across them can be sophisticated, can be slow, can lead to bugs. So we've been working really hard on improving the APIs for that so that you can distribute your training across multiple devices, be it multiple cores in a TPU, multiple GPUs, those kind of things. So we realized that folks who really want to go out there and train state-of-the-art models, instead of working on a single GPU and spending many hours or many days training it, really to give you the ability to distribute your training effectively. And then the second one that's particularly exciting is this one's, we all are NumPy developers at some way or another. When we start using TensorFlow and we start going into machine learning, I never used NumPy before I was in machine learning, and now it's a valuable part of my toolkit. And one of the things we want to do is to bring NumPy APIs and TensorFlow closer together. So instead of you needing one set of libraries or one set of code to maybe manage your data in NumPy, what if we could have the NumPy code as part of the TensorFlow code and like just leverage some of the economies of scale that will come out of that in a similar way to when Keras became part of TensorFlow. It made it a lot easier for us as Keras developers to be able to use TensorFlow. This is experimental at the moment. We're working really, really hard on it, but it's a particularly exciting part of the release. And so there's others that I've mentioned here. If you're a GPU user, an NVIDIA GPU user, TensorFlow now runs with CUDA 11 and CUDNN by default. And if you are a Keras functional API user, so if you're familiar with using Keras for building models, and I'm going to be showing some code of that later, when you get started with Keras, you tend to build what are called sequential models, where all of the layers in your model are defined in a sequence, and data goes in, gets processed through all the layers, and then comes out at the other end. But when you start getting into some more exotic model types, like generative adversarial networks, as an example, just having a sequential model like this isn't enough. You might have multiple models talking to each other. You might have models that branch and have multiple outputs. You can have models with multiple types of input. And the Keras functional API is what you use to design that. It's very similar to the sequential API, but just that little bit more flexible so that you can have those more exotic models. And with 2.4, we've had an internal refactor of the Keras functional API. So the idea there is that if you're already writing code with the functional API, you don't need to write your code. It's not breaking changes, but we've refactored it internally to really improve the reliability, stability, and performance. So that's the high level of what we've been working on with 2.4 and the release of 2.4, and right now we're hard at work on version 2.5. So the overall TensorFlow ecosystem, it's designed to really bring things from research to production, to deploy them everywhere, while also empowering responsible AI. So we're not all researchers, very few of us are, but many of us do build models and we want to bring them to production and deploy them. But I would just like to show a little bit about what's going on with research. And some of the stuff that's happening in research I find particularly exciting. So here's a few examples of some cutting edge research that has been empowered by TensorFlow 2.x. On the left, you may have seen these models that are used for detecting people's poses. And there's a common model called PoseNet. Well, this research has actually taken that to the next level, and instead of just poses, for people who know how to use sign language to speak, to actually do sign language detection using the pose and using details from the image. And you can see as this person she's actually doing sign language, that we were able to get real-time sign language detection using a unified text-to-text transformer. In the middle, if you're doing reinforcement learning, one of the things with reinforcement learning that can be difficult to do is to scale it. So there was research out there about how to scale reinforcement learning with this architecture called Seed-RL. And again, to me, it's an interesting one that some of the cutting edge things that we've seen out of research, like you've probably seen famous things where now AIs are beating like top games players at games such as Go. Reinforcement learning is at the core of that, but to be able to scale that, it's something that it's still a largely unknown territory, and there's a lot of research going on in that space. And then perhaps most exciting is quantum computing. And quantum computing continues to be driven forward. Google, we have our own quantum computing folks. And we see there's an archive paper here about reinforcement learning, but to be able to do reinforcement learning using quantum variational circuits, and how TensorFlow has been able to work with that. So, the core of what I want to drive here is that cutting edge research into new techniques or into new ways of using AI, that TensorFlow is really at the heart of that. There's also been lots of add-ons that have come out of our research group. So sometimes the artifact isn't just to do research and to write a paper and to publish the paper, but to actually productize that work and turn that into things that are available to the TensorFlow community. And there's a bunch of them that I'm showing here. And one of the ones I find most exciting is the 3D. And as you can see from the graphic here of this rotating model, so that to be able to build image classifiers or scene recognizers that don't just recognize the pixels in the image, but may actually even be able to recognize the depth in the image, so that you can start learning about environments in 3 dimensions instead of it from a 2-dimensional image. And when you think about a lot of the research that's done in things like self-driving cars or anything where decision-making is based on an image, being able to decide based on the entire scene, including its depth, will certainly allow us to make much smarter things. A lot of the research models, of course, are migrating to TensorFlow 2. So a couple that came out recently are object detection API. Object detection is a very difficult problem to solve, and it uses exotic models like I spoke about earlier on, where you don't just have a simple sequential model, but at the very least with an object detection API, you've got multiple inputs and multiple outputs. The multiple outputs you can see on the picture on the left here, where one output was the image that it sees and what that is an image of, be it a kite or a person. Another output of the model is the bounding box and the location of that. So imagine training a model, you have to do the same thing, multiple inputs and outputs. It ends up being very difficult, very code intensive to do something like that. So we wanted to simplify that with the object detection API. We're still continuing to work on that. And another one that's relatively recent that we're really excited about is the recommender system. Like one usage of AI, that we see very often is people building recommender systems. And if you don't know what that is, think about it as if you've ever done online shopping, and it might be, and it understands the habits of things that you bought, so it can suggest new things. That's an example of a recommender system. Building them is complex and hard. So what we want to do is to try and make that as easy as possible. And part of that is to release a recommender system API. We can see here, that's the idea behind it. The URL is here, tensorflow.org/recommenders, and it's built on TensorFlow 2 and Keras, so it makes it easy, high-level coding. And one of the things as well is to be able to bring this to production with something like TensorFlow Serving. So that was research. I'd also like to talk a little bit about going to production. And a new thing for production and be able to take you to production that we've been working on is TensorFlow Cloud. So now the idea behind TensorFlow Cloud is to give you cloud scalability as a developer easily. So if you look at the code that's on this slide, this top box is a very familiar code if you're a machine learning person, where this is to build a very simple sequential, Keras sequential here model for recognizing the MNIST digits, and these are common handwriting digits where you can quickly and easily build a classifier that recognizes handwriting. But it's this piece of line at the bottom is what's new. The idea behind this one is that to offload the training from your development box into the cloud with a single line of code and a single function. Now, with something like MNIST, it's pretty simple. You really wouldn't need to do that. But think about if you're building a giant model, and think about the complexity of building a giant model. And you don't want to get into distribution strategy to be able to hand code yourself, to be able to go across multiple like GPUs or TPUs and those kind of things. The idea here is to try and offload your training workload to cloud. We're still working on it. It's not going to work on every model all the time, but it's another option for developers in particular to speed up your training process so you can rapidly iterate on your models. I mentioned a few times TPUs, and with TensorFlow, we're continuing to support TPUs. If you're not familiar with these, the TLDR of a TPU is, if you think about a CPU on your computer, the CPU is designed to be a general purpose chip to do anything, managing the keyboard, managing the network stack, and all of these kind of things. A GPU is a specialized chip which was originally invented for gaming to do things such as matrix multiplication and floating point multiplication really quickly, because that's the important tasks in gaming. By an amazing coincidence that those are also the important tasks in machine learning. So when you use a GPU, if you can offload the floating point multiplication, the matrix multiplications, those kind of things to a GPU, you can really speed up your machine learning because the CPU wasn't really designed for that. We then realized that if we build a specific type of chip called a TPU, where the T stands for tensor, a tensor processing unit, you can optimize even further. And you can do things, for example, like if you reduce some of the precision, so instead of using a floating point, in some cases, you can actually just use an 8-bit integer. And if you have chips that are dedicated towards the mathematics of 8-bit integers, as an example, then you can optimize your training even further, and you can train even faster. So we've been working on building and making TPUs available to people. But as a result, it's one thing to make the hardware available, it's another thing to give you the APIs that will allow you to use that hardware and to make the most of that. And that's what we've been working on in TensorFlow 2. And then, of course, there's not much point being able to build state-of-the-art models or build cool models to solve problems if you've got nowhere to deploy them. So we're focusing very much on deployment. And my personal focus this year is really being about deployment and empowering mobile developers and web developers in particular. And the technology behind this is TensorFlow Lite. Now, TensorFlow Lite is more than just a light version of the runtime. When you get a model and you want to run it on a small device like a cell phone, one of the things is that you're running in a very constrained environment. A cell phone has a battery. A cell phone is a personal device that somebody is using, and that private data, you don't want it to be able to leak out to the cloud. It's also a personal device that somebody's using, and you don't want to eat up all of their resources. So the idea behind TensorFlow Lite is a set of tools that will allow you to convert your models to make them mobile friendly. So, you know, they're privacy preserving, they're battery preserving, they've got low latency so that you can build apps that will run inference without heating up your phone and those kind of things, as well as, of course, the inference engine itself that will run on Android, run on iOS, and also run in like micro Linux and micro Python environments, so like things like Raspberry Pi. And then there's TensorFlow JS, which is really exciting that, you know, not just for running inference in the browser, but also allowing you to train models should you want to. And we've been working with the community who've been just building the most amazing and fun demos. There's a few of them here about not just when you can use a model in the browser, but then integrate that with other cool web APIs that are out in the browser. And one of my personal favorites, the one that you can see here, the Mona Lisa effect, go check it out. There's an urban legend that the Mona Lisa's eyes follow you, so that no matter where you are in the room, she's still looking at you. And this demo, in a funny way, leans into that so that it uses the webcam. The webcam uses a model to detect where you are in the frame. Like right now, I'm in the center of the frame, but if I move over here, I'm now on the side of the frame, and it will actually have the Mona Lisa's head move to follow you. And it's very cool. It's also slightly spooky, but it's a lot of fun. And of course, we're using on-device ML at Google ourselves with TensorFlow Lite. Some of the things, some of the apps that we've built that you can see here. One of my personal favorites on the left-hand side is the Hold for Me with the Pixel 5 or the Pixel 4a, where it's effectively like a little agent that will answer the phone for you, that will have a conversation with the person for you, and then will inform you that, hey, this person has called you, they want to talk about this. Do you want to take the call or not? It's a little bit friendlier than a standard answering machine because, you know, you're on the other side of it and you can choose whether to accept the person or not. And it's basically become that personal assistant for you in your phone. And it's powered by machine learning and powered by TensorFlow. It's pretty cool. So TensorFlow Lite that I've mentioned, we've worked really hard on that with many, many improvements. There's a lot of them on this slide here. I'm not going to talk about all of them, but there's a couple that I would just like to drill into. And the first one is in the conversion space over here. So earlier I said, like, you know, you use TensorFlow to build large models, state-of-the-art models, models to solve machine learning problems. But when you convert it to run on a device, you have to, you know, you have to understand that the runtime of that device has different constraints than the runtime on a server or on your development box. So there's a lot of conversion that needs to be done. And one of the things that if you're familiar with natural language processing in particular, there are model types or layer types called LSTMs and RNNs that are pretty sophisticated layer types, and they're very sophisticated math that's going on in them to be able to recognize things such as sequences. So as part of the conversion, we realized that we can really double down there and improve them, make them smaller, make them faster, make them use less battery. And that's one of the things that we've been working on in TensorFlow Lite. And then this column here, the model optimization in the same way, is that, okay, how do we optimize our models? Do we make them faster? How do we make them smaller? But we can do this at all stages of the pipeline. We don't just have to do it after the model has been trained. We can start thinking about things like quantization aware training. So if we're going to build a model and we know that we're going to shrink it to run on TensorFlow Lite, what can we do as part of the design of the model and the training of the model itself to better prepare for that, to get better results? And things like that we've been working hard on TensorFlow Lite, and, you know, continuing to hopefully improve it every day, and hope that you can get great results out of it every day. Then there's responsible AI, and I just want to talk quickly about that like there's really no point in being able to build great models and deploy them if they're used irresponsibly, and often they can be used irresponsibly unintentionally. And what we want to do is to really make it easier for you to ensure that they're not used irresponsibly or unintentionally. So there's a bunch of tools that we've been working on and a set of principles and practices that will help you to build AI for everybody. So we've published recommended best practices, we've tools for fairness and interpretability, and we've also got tools for privacy and security. Like one of the important things with responsible API is keeping your users' data private, so that if they're using this data, like maybe photographs that they're taking, and they're using this with machine learning models, you want to ensure that these photographs are kept private. So part of the overall workflow for machine learning has these multiple stages: defining a problem, constructing, preparing your data, building and training the model, deploying and iterating. And there's a number of different places where you should be asking questions about not just the model, but the process of building the model. And we're trying to make tools to help you answer these questions, so that if you're answering these questions effectively, then you're reducing the chance that you would build AI that could be used irresponsibly. There's a whole bunch of them here, but I'll just focus, like, for example, on one here. Am I using a representative data set? Often data gets the blame, that if we build models that, work better for one class of people than they do for another, we can turn around and say, well, that's not our fault, that's the only data that we had. Or we didn't recognize it at the time that we were training it, that we only had data for tall people and not for short people, or for white people and not for black people. But the idea is, like, if we give people the tools to help them understand their data set and see that they're using a fully representative data set, or if there's complexities in the data where it's not as simple as the examples that I just mentioned, but that there are intersections going on within the data that leave people out, then tools to be able to understand that, to see if you're using a representative data set, are important. So we've been working on a tool set like that one as an example. But look at all the questions here, look at all the things that you may need to answer. Okay, so quickly, I know we're running short on time. We're also looking at TF privacy. So the whole idea is, tackling issues like privacy is not a one-size-fits-all task. And TF privacy's new functionality, the goal here is to assess your model's privacy. So training with privacy is not always possible. People might need to share data to allow you to train models. For example, if you've got a distributed set of users who are taking photos and sharing them, we want to be able to train data like that while maintaining that kind of privacy. And with the TF privacy tools, one of the things is we want you to help to measure a model's privacy without continually retraining it, so that they would need to supply you with more data, those type of things. And one of my personal favorites is the model card toolkit, so that this automates transparency reporting. And it's a little bit small on this slide at the moment, but if I show here, for example, in a training set that was shown here, and in the training set's in green and the evaluation set's in blue, what this did when it trained this model, and on the right-hand side, these two bar charts are gender. And we realize, like, when we look at this model card toolkit, is like, instead of just seeing a number of female and male, when it's represented like this, we realize that women are underrepresented, not just in the training data set, but in the evaluation data set. So in using this model and using it in the scenario of, like, a woman, maybe it's, I don't know, the image recognition or something along those lines, then of course it's going to perform worse for women than it will for men. And on the left here, it's races that we used in this one. The big bar at the bottom was white people. The next bar, which is much smaller, but still the second biggest, was for black folks. And then these other bars that are tiny are for races such as Native Americans, Eskimo, Pacific Islanders, and those kind of things. And we can see here that this data set was very poorly representative of the diversity of the people around us. But being able to recognize that, understand that, identify that will help us to fix that. So the TensorFlow toolkit, the responsible AI for it, is available at this URL, tensorflow.org/resources/responsible-AI. And then finally, just really, and the most important part is really the machine learning community. We're trying to build an ecosystem. We're trying to build a product that really will make you successful. And your feedback, your contributions, the things that you've been building, the way that you've been stretching the framework for us is really what makes all of this possible. So just, on behalf of everybody at Google, I do want to thank you for that. But we also want to try and make it easier for you to do your jobs. And like one thing that we've learned from the community is that it's great to be able to build models, but if we can't share them effectively, and if we have to compile a model and put it on GitHub and then someone else downloads it and then uses it, it might be hard to see the results and it might be hard to collaborate. So tensorboard.dev was designed with that in mind. where you can actually share your model. You get a deep link to a TensorBoard of your model, and that's showing like how your model is behaving, maybe how it's training, how it's behaving, how it's doing inference, those kind of things. And this was just a tweet that went out of like, like be able to share these TensorBoard.dev instances with a deep link into it. And we're really excited to see how researchers are using it. Like in this case, this person was like, there were 550 curves that they were able to find in their research. They didn't fit that into a paper, so they want to be able to access those raw metrics and share those raw metrics so other people could explore them further. The community has also really been immensely helpful in translation and localization, and we really thank you for that. So, for example, our Jupyter notebooks with samples has community translation support, and it's currently 13 languages. And then the guides and tutorials and documentation, there's a lot of translation efforts going on in there. Japanese, Korean, simplified Chinese were released, and there's a lot more still to come. And beyond product updates, the heart of what we do is we want to try to help to bring people together to solve AI and ML challenges. The type of events looks a little different. Like today's event, I'm sitting in my office talking to a blank screen instead of a room with all of you. But the nice thing is we're still being able to do community, but we're really looking forward to what the future looks like, where we can be closer in community. There's a few examples here of some fun events that were done. I was involved in one in Korea in the bottom left. It was a boot camp for Korean students, and yeah, it's so great to see the entire world embracing AI and ML, and we're really privileged to be a part of that. There's TensorFlow user groups going on around the world. You can see a few of them here in the pins on the map. We've had summits like with the TFUG in India. We had a great summit last year, and if you're interested in being a part of a TFUG or creating one, email the TFUG help@tensorflow.org address that you can see at the bottom here. There's also special interest groups. There's 14 of them, and we've been continuing to grow the special interest groups. And these are led by members of the open source community, such as our fantastic Google developer experts. So if there's a particular part of TensorFlow that you're interested in, be it MLIR or Swift or Keras or any of those, there's a special interest group for you. I mentioned a moment ago our Google developer experts. We love our GDEs. We have like over 165 of them, and what GDEs do is they're giving tech talks, running workshops, and they're really an independent voice for developers worldwide. And we're just ecstatic to have GDEs, and we'd love to work with you. If any of you are watching, thank you so much. And you can see some of the collaborative projects that we've been working on, such as like AI versus COVID, and which was really driven by our GDEs. With the reinvigorated racial justice movements in the US and around the world, one of the things that we've been wanting to do is to support the Black in AI community. I've been working on this one myself, and so things such as funding faculty and supporting content at historically Black colleges and universities, donating to Black in AI, which is a nonprofit group to support and to encourage the use of AI in the Black community, funding and providing content to the chapters of AI in Africa, and maybe some of you are present today. And I teach courses on Coursera, and one of the things to work hard to offer stipends at Coursera, so offer credits to Coursera so you can access the content for free, and then offer stipends to our certificate exam so that you can show that you're a qualified TensorFlow developer to help you either grow or change your career, to show that you're an AI using the TensorFlow certificate, which is this. And so the idea with the TensorFlow certificate, we've got almost, I believe it's about 2,000 people now, or close to 2,000 people globally have passed this. And the goal is to get the key skills in TensorFlow and the key skills in machine learning, and to have a community of people who are demonstrated that they're proficient at that, to help employers find good people and help good people find employment. So again, we're doing our best to widen access to that. So for people of diverse backgrounds and experiences, there are stipends out there. If you're interested in becoming a part of this, we have the budgets that I mentioned on the previous slide to really provide scholarships to Coursera and to provide stipends to help cover the certificate costs. So thoroughly encourage you to apply. So that's it. This is where the keynote wraps up, and we're going to take a very short break because I ran a little bit over time there, and then I'm going to jump into the Zero to Hero talk, and then I'll take questions at the end.
Awesome, Lawrence. Thank you very much for that keynote. I have my own questions as well, so I think I'll use my privilege a little bit to ask a few questions. So from research to production, and now we're seeing TensorFlow Cloud. What are the, I mean, in very simple terms, what are some of the biggest problems or inconveniences is TensorFlow Cloud solving for people who are just getting started with building machine learning models?
It's a great question, and I think there's two big. Sorry, my sound dropped out for a moment. So there's two big ones that I think it solves. First one is giving you easy access to scalability, and you can do distributed training with distributed strategy that I spoke about earlier on, but the underlying infrastructure can be hard. Getting access to a bunch of TPUs and then getting your TensorFlow model to train across those TPUs has a number of different hoops that you need to jump through. Just getting access to the CPUs, understanding the addresses, TPUs, understanding the addresses of them, and then building your code to be able to train across all of them. It's very powerful, but there's things that you have to do. There's work that you have to do to get that to work. So the TensorFlow Cloud, part of the aim of that is to make that easier. And as you saw, it was a single line of code here where it was like, okay, here's your cloud nodes that you've set up, one line of code, and it will train across all of them. And then that's also the second part, because accessing stuff on cloud can involve you jumping through a lot of hoops, creating a cloud account, creating virtual machines, configuring those virtual machines for TensorFlow, picking, setting up a system of 10 virtual machines, all of them having the same versions of TensorFlow and being able to train across all of them, and to try and reduce that complexity to the developer, so that you say, I just want to code my model. I don't really want to jump through all these infrastructure hoops. So those are two of the big things that I think TensorFlow Cloud will help with. There's more on the way, but as we're continuing to build and drive the program, but I would say those are the two immediate advantages. Did we lose you? Okay. So I see there's another question.
Speaking of more on the way, we already have interest in what's new or what we expect in TensorFlow 2.5.
So we want to keep the surprise there. So I can't, we are continuing to work on it, but I will say the big thing that
Go ahead, Lawrence.
we want to push forward with. Sorry, I don't know how well you can hear me. So with TensorFlow 2.5, one of the things we're not allowed to speculate too much about the future, but I will say with TensorFlow 2.5, the thing that we're working hardest on is quality, and to really drive improvements to the API surface, to drive improvements to training, and to drive improvements in the overall developer experience. So we're still hard at work on it. We're hoping to have some announcements around that in the next couple of months. Are there any more questions? Okay, shall I skip to the next presentation then? Oh,
there was one question. Is there a way to train your model on Colab with VS Code?
I don't think so. So, I mean, of course, in Colab, the idea is that you have a browser-based environment like a Jupyter Notebook that gives you, beyond just the Jupyter Notebook, though, it gives you the hardware on the back end. You can use TPUs and you can use GPUs. So I guess the core of this question is, can you get access to that back-end infrastructure if you're coding in VS Code? My understanding of that, at least at now, is no. That if you want to be able to use the Colab back-end infrastructure, you still have to be using Colab within the browser and the Jupyter Notebook within the browser. And the primary reason for that is the GPU and TPU resources are not unlimited. And so one has to be signed into the browser with their Google accounts to be able to get their allocation of a GPU or get their allocation of a TPU, so that you wouldn't have somebody spawning up 1,000 instances of a browser and using 1,000 GPUs, that type of thing. So yeah, unfortunately, as of now, no, you would still have to use the Colab Jupyter Notebook environment. And I see Derek has also asked, when will Colab Pro be available in SSA? I honestly don't know. That's a decision from the business folks. Yeah, I'm sorry. I generally just work on the technical stuff, but I'll certainly take the feedback back to them that I know you want it, and I know everybody wants it. It's terrific. And for those who are not familiar with it, Colab Pro is a subscription version of Colab, which gives you like more time with the GPU. There's earlier I mentioned you have to sign in.
Thanks a lot, Lawrence. Very grateful that you were going to give us 2 talks, so I think you can go straight into the second talk.
Okay, sounds good. And let me go straight into that. Can you see my slides? Are you able to see my slides? There we go. Alrighty. So second talk I'm going to do is really zero to hero with TensorFlow. I know we're running a little bit behind schedule, so I'm just going to get right into it. So the idea with machine learning. So the idea with machine learning is that it doesn't have to be complicated, first of all. And often when we start looking at machine learning for the first time, we can be turned off by lots of math and lots of calculus and all of these kind of things. But the reality of machine learning is that it's really not that difficult. And I want to talk about this in terms of coding and what it's like for coders. So if we look at traditional software development, you know, I like to kind of look at it in this way where you write rules, those rules act on data, and they give you answers. So for example, if you work in finance, there's a common analytic in finance called the P/E ratio, which is price over earnings. Are my slides gone? I'll just keep talking, but if we can get the slides back up. So there's a common analytic called price over earnings. And the idea behind price over earnings is that, you know, you'll have data, which is the earnings of a stock and the price of a stock. You'll have rules that you then apply to that, which is just divide one by the other, and then you'll give an answer, which is that analytic. So this is like what we do as coders. We write code to provide answers based off of data. Or another example is if you're playing a game. So we're all familiar with it, like the bricks game or breakout, as it's sometimes called. And you'll write code, and again, there's data here, the location of the ball, the location of the brick. There are rules that you say that, hey, if the ball collides with the brick, you want to take this action. And then there's answers like removing the brick, updating the score, and changing the trajectory of the ball. So these are all things, again, we're writing rules. Those rules are acting on data, and they're providing answers. And I always like to summarize that in a high-level diagram like this one. The traditional programming is we're putting in rules. Those rules are acting on data, and we're getting answers out of it. And as coders, you know, our jobs have always been to try and figure out the best rules. How do we write them most efficiently? How do we write them so that they operate quickly? Now, the idea behind machine learning is it's a similar diagram, but things have been turned around a little bit. So instead of us trying to figure out the rules that will act on the data to give us the answers, what if we already have the answers and we have the data and we want a computer to figure out those rules? Now, that might seem a little bit abstract, so let me show a scenario where I think this really works, and hopefully will make it clear. Imagine if you're building some kind of activity detector, like you're building a fitness device, like a watch that determines your activity so that you can, like, you know, monitor your fitness and things like that. Think about what the code inside this would look like. So, for example, if somebody is walking, you know, you could say, well, we have an accelerometer on the device that gives us the speed. And we could say, hey, if the speed's less than a certain amount, they're walking. We go, great. What if they're running? Then we can say the same thing. It's like, well, if the speed's less than 4, they're walking. Otherwise, we could say that they're running. We're writing rules. And then it's like, okay, well, what if they're biking? Well, we could still use the speed there. It's a naive algorithm, but it kind of works that if their speed's below a certain amount, they're walking. If it's below another certain amount, they're running. And then if it's above that, they're probably biking. So we can say, again, rules that we can create can allow us to determine this. So this kind of works. But then what if they're golfing or some other sports that aren't so easily determined just based on speed? How would we create the rules for that? It would be impossible. The amount of code that would have to write to maybe determine how they're moving their arms, and they're standing still and then they're moving, and all of these kind of things, it's very, very difficult for us to write code. It would be infeasible for us to do this. So this is where machine learning comes in, to think about problems where it's hard for us to create the rules ourselves to solve the problem. I used activity detection a moment ago, but think about things like computer vision or natural language processing. You know, with computer vision, like what is in an image, if you have a bunch of rules that you're writing that look at the pixels in the image, it's hard for you to determine if that's a cat or a dog or those kind of things. But computers are very good at pattern matching. So for example, if I go back to the activity recognition, you know, and then I've gathered all of the data from all of the sensors on the device, and I said, okay, here's the data and the person is walking. This is what walking looks like. Here's the data when the person is running. This is what running looks like. A computer might be good at seeing some of the patterns in that data that are always present and only present or mostly present when the person is doing that activity. So for example, here it's like, well, these patterns of ones and zeros only happen when the person's walking. And if we look at the data in that chunk, and it's like, well, when they're running, it's different. When they're biking, it's different. When they're golfing, it's different. So now computers are able to kind of sift through the data, find those patterns, and then assign those patterns to those labels. And now in the future, when we see those patterns, the computer is able to infer that the person is doing that particular activity. And that's all machine learning is. It's that kind of really, really fancy pattern matching. Now, how do you do pattern matching algorithmically? Well, the first thing that you're going to do is you're going to make a guess, right? You're going to say that I think this person is walking. And you know, you're going to look at maybe 100,000 instances of the data. You're going to make a guess that when the data looks like this, the person's walking. When it looks like that, they're biking. Those kind of things. Then you're going to measure the accuracy of that guess. You say, okay, well, I think this piece of data determines it. Let's go through all of them. Let's measure how accurate we are with that guess and how good or how bad it is. And then once you have that data of how good your guess is, how bad your guess is, where it works, where it doesn't, then you can optimize your guess. And once you've done that, you can go back and do it all over again and repeat it. And that's really the machine learning paradigm. You start by making a guess, you measure the accuracy of that guess, you optimize it, and then you continue. With the logic being, particularly in the optimizer, that the more times you go through this cycle, the better the guess becomes. And here's where all that fancy math, all that calculus, and all of those kind of things are going on. Things like there's a term called gradient descent that you might have heard of. And that's all in this optimizer of really trying to improve your guesses and improve the pattern matching that's going on within the data. But the nice thing is with TensorFlow, you don't have to write all of that code. You don't have to understand the calculus. If you do, you could probably write better code. But to be able to get started, to be able to be successful, you don't need to understand it. So if I go back to this paradigm, now it's a case of labels, which are our answers. That's like the person's walking, biking, running, or this is a picture of a cat, or you know, this sentence is positive sentiment. Those kind of things are the labels. The data is the data itself. And the machine learning goes through that cycle that I mentioned earlier on to come up with a set of rules, and that ends up building something called a model. So now that model that you have is this binary blob containing all of these rules. So in the future, if you put data into it, it does the pattern matching within that data, and it gives you out an inference of what it thinks is going on. So for example, in the activity environment, the activity detector I spoke about a moment ago, we could be passing in a blob of data, and then the model would say, I think this person is walking, biking, running. So that's kind of abstract. So let's kind of put this idea of pattern matching into practice so we can see how it could be used, for example, in computer vision. So if I give an image to a computer, all the computer sees is a bunch of pixels. It doesn't understand anything about the contents. So to simulate that, I've taken a picture here and I've blurred it, so you probably don't know what it is. And so in the same way as a computer has no idea what it is, it just sees a bunch of pixels. But with images and image processing, there's a thing that you can do. And if you've used Instagram or Photoshop or something like that, you've probably heard of filters. Now, filters can be used to change an image, but they can also be used to highlight items or elements within an image that we're going to call features. So for example, if there's a specific filter that I could apply to this image that resulted in this, I could say that this is detecting this feature. Now, to you and me, these two things, they look like human legs, right? And so we say they may not be. It might be two tree trunks. It might be two cylinders, but you know, this kind of looks like human legs. And a filter that changes the image to this and regularly changes the image to this to detect something like this, we could say is a feature detector, in this case for human legs. There might be another feature that detects these things. And now, again, to you and me, they look like human hands. And then another one that maybe detects this, and this looks like a human face. So if over time you had a bunch of filters that you could apply to an image that detected these three things, you know, like this with legs plus hands plus a face, and I had already said to the computer that this image contains a human, now the computer can start saying, well, if I have a filter that I pass on the image and these three things show up and it's a human, now I'm starting to pattern match that this is actually a human. And I say, okay, what if you want to distinguish something else and say we want to build an image that just determines whether something's a human or a horse? Then you could have a different set of filters that apply to the horse that detects these things, which are very different legs than a horse, or a horse has very distinctive ears and a horse has a very different looking face. So if I've gotten a bunch of images that I've labeled as a human and another bunch of images that I've labeled as a horse, and I've got sets of filters that I can apply to these images that detect features, but when one set of features is detected for something that's labeled a horse and another set of features is detected for something that's labeled a human, I now have the beginning of an algorithm that can tell me the difference between a human or a horse. So filters will extract these features like human hands or horse's ears and those kind of things. And then when I combine these filters with the labels, I can start making a prediction of the contents of the image. And the filters that match a label can be learned over time. Remember earlier I was saying we make a guess, we measure the accuracy of that guess, and we optimize that guess. Well, we've no idea what those filters are. They could be just randomly initialized filters, and all a filter is a mathematical transform that's applied to an image. So they could be initialized with random numbers, passed over all the images, features extracted from them. Those features might be complete nonsense in the beginning, but there might be some that are very deterministic of a human and some that are very deterministic of a horse. And then over time, as we improve and learn those filters, now we could end up having an image classifier that sees the difference between a human and a horse. And we end up with the same model. So for example, if I have an image like this one, and we've spotted what look like human legs, and we've spotted what look like human hands and a human head, but this image wasn't previously labeled as a human, we pass that image into the model applies all its filters, it detects these things, and it says, well, when I detect those things, this is a human. And as a result, we now have built a very simple concept of computer vision, where instead of a whole bunch of pixels being thrown to the computer that it doesn't understand, it actually recognizes there is a human in this image. And it's the same paradigm. In this case, it's the filters are our guess. We randomly initialize a bunch of filters. We measure the accuracy of them against the known examples. We optimize and we continue. So let's look at what that looks like in code. So I'm just going to skip forward. In that case, it recognizes a human. So this is what it looks like in code. So in the keynote earlier, I spoke about Keras sequential models, and Keras sequential models are a great way of getting started. And this is a Keras sequential model. So within this model, I've got a bunch of layers, and one of these layers is called a conv2D. Now this stands for two-dimensional convolution, but just see that as a filter. Convolution is just a fancy word for filter. And in this case, in my first layer, I'm saying I'm going to create 16 filters. So my image is going to have 16 filters applied to it, and let's see what we can get out of them. And in the next layer, and then in the next layer, there are 32 filters, and in the next layer, there are 64. So what's happening is my image is going to be filtered 16 times. Each of those 16 is going to be filtered 32 times, and each of the results of that is going to be filtered 64 times. So we're going to end up with lots and lots and lots of images and lots of filters applied to that to help us pick out the set. Now, one of the things about this is that if I have like 1,000 images that I'm training with, these 1,000 images on every loop around are going to be filtered 16 times to produce 16,000 images. Each of those 16,000 then are going to be filtered 32 times, and the results of that are going to be filtered 64 times. We're going to end up with lots of images and lots of filters that we're applying to those images. And this is one of the reasons why machine learning can be pretty slow. So applying things like a GPU or TPU to speed it up is essential. But another little trick that we can do is this thing called max pooling. And the idea behind max pooling is that when you see 2, like this, is basically you're halving the size of the image on each axis. So what you're going to do is, like, first time I come in, I have 1,000 images. I'm going to apply 16 filters to them to get 16,000 images. But when I max pool that, the idea is that those 16,000 images are now going to be quartered in size before they're fed to the next filter layer. So as a result, I can use less memory. And one of the things that we've discovered about using these kind of pooling is that when you've applied the filter to the image to extract the features, and then you quarter the size of the image, for the most part, you don't lose the features. So you're able to compress your image while maintaining the features that have been detected in the image, and so on as you go through the layers. So this is a way that you can manage your images to make them smaller, to use less data in your infrastructure. At the bottom here is a dense. If you've ever done any kind of neural networks, if you've ever seen any kind of neural network diagram, you've always seen these blobs with all these lines connecting to each other. That's densely connected, and that's what this is called, a dense, and that's generally used for doing the pattern matching. So this top part is to learn all of the filters, and then this bottom part, the dense, is to say, okay, here's the results of the filters. Now I'm going to match them to things like, to labels like horse or human, cat or dog, diseased or not diseased, or whatever it is that we're actually building a model for. And then the final dense layer, and it's always the most important when you get started, I'd say, to look at the very last one. This ends up telling us what the neural network is going to learn, or how many things it's going to learn. And the number at the bottom here, in this case, it's a 1. There's a special case for 1, which I'll explain in a moment. But the number here at the bottom is generally the number of classes that your network is designed to detect. You know, if it can determine 1,000 different types of food, you'll see 1,000 here. The one special exception is if you're only detecting 2 classes, in this case I am horse or human, you can do that with a single neuron. That's why there's only a 1, where the value drives towards 0 for one class or 1 for the other class. Then comes the, when you've defined the model, you want to define how it behaves while it's actually training. Remember this diagram, make a guess, measure your accuracy, optimize your guess. So measuring your accuracy comes in something called a loss function. So instead of you having to write all the code to measure the accuracy, researchers have come up with a number of different algorithms for doing this. And all you have to do is pick your algorithm and say, I want to use an algorithm in this case called binary cross entropy. And part of the learning curve for you as a machine learning engineer is picking the right algorithm for the right task. Often the clue is in the name. You can see here I'm detecting two different things, a horse or a human. It's a binary problem. Hey, there's a loss function called binary cross entropy. And as a result, you can experiment with different loss functions to check on your results and that kind of thing. But you know, there's a lot of trial and error if you don't understand the underlying math. But fortunately, it's pretty quick for you to do that kind of trial and error. And then the optimize your guess comes in the optimizer function. And in this case, I have an optimizer that I'm using called RMS prop, root mean square propagation. But again, there are many optimizers out there. You can experiment with different ones for different results. And then once you've picked and compiled your model with the loss function in the optimizer, you're going to train it. You'll see this thing called epochs equals when you're actually training. And that's just the number of times you're going to go around the loop. Like in this case, I've designed this, this code is just going to go through that loop 12 times. And I'm going to demo that right now. So to show how to train a model for horses versus humans. So give me one moment. I'm going to share a different screen. Let's stop that one and let me share a different browser. And this is one that I trained earlier. Is my screen showing? Can we have my screen show, please? Sorry. There we go. Oh, it was there for a moment. There we go. All right, let me zoom in a little bit on that. Oh, it's gone again. All right, here we go. So I'm showing in Colab here. This is a model that I trained earlier on, and you can try this Colab out for yourself. Oh, we've lost my screen again. There it is. If we could full screen this so that it's easier to read, that would be really good. There we go. Okay, and let me zoom in a little bit so make it easier for folks to read. So this was the model that I showed in my slides for training horses versus human. And I trained it like just earlier this morning, I think for about 15 epochs. One of the things I want to show is we've created that convolutional neural network that I was showing in the slides. But look at the thinking in terms of the flow that I was talking about earlier on. You create a guess, you measure the accuracy of that guess, you optimize, and you continue. In the first epoch, it reported to me that it was accuracy of 50%. So that's where you can see it's like generating the guess. If you're going to guess this is a horse or this is a human, you're going to get it right 50% of the time based on a random initialized guess. So it made that guess, it measured the filters that it had and looked at the loss around those filters and the accuracy around that, and then it optimized for the next guess. So we went through the loop again, and then when we went through the loop again, it was like it went up to 68%. As you can see here, it was like the guess was like now almost 70% true. It optimized, went through the loop again, then it became 91% true. And by the time we'd gone through it like 15 times, you know, it was at 99.81%, at least on the training data. So it got to be really, really good at looking at this training data to be able to understand, I now know a set of filters that can determine the difference between a horse or a human. Now that's just on the training data. Now, obviously in the real world, when you show it a picture of a horse or a human, it's not going to be on the training data. So one of the things that I did was to use another set for validation. And here we're going to see problems in this validation set. And this is a thing called overfitting. And we can talk about overfitting in another time. But the idea here is that it became really, really good on the training set, but not so good on the validation set. And as you can see, the validation set was like 80%, 70%, that kind of thing. I'm surprised it just went down to 50% in this case, because usually the validation on this one's about 80%. And if I run this, I'm going to go in and I'm going to like run this. And what I'm doing now is I'm going to upload a bunch of images. And you know, these images I have on my file system. Okay, give me a moment. I'm going to upload each of these images. And these images are going to be converted into tensors. Those tensors are going to be passed into the model, and then a prediction based around that is going to be given. Now, there's a clue in the file name for us so that we know what it actually is. So we'll see here, like for the very first one, it was called whitehorse.jpg, and it went through and it gave it the classifier, passed that image through the convolutions, through the filters, tried to apply it to a label, and gave a score. Now, remember earlier I was saying if the score is close to 0, it's a horse. If it's close to 1, then it's a human. So the score it gave this one is like 7 times 10 to the minus 10. So of course, clearly this was a horse. The second image, we know it's a horse based on the file name. The detector was also able to see that it was a horse. And if I go down a little bit, like this one, for example, was detected as a horse, even though it was a woman. And this part of this is because I was overfitting on these images. So this is a model that will need to be continually refined, but we can see how all of this is working. And for a little bit of fun, I'll show you that image that it thought was a horse when it was actually a woman. And because when earlier I was detecting, I was describing that features to be detected. Oh, we can't see it. Let me share that. I'm going to stop this one, and then I'll go to Q&A. And let me share just for a little fun. The image that it detected as a horse was actually this one. And remember earlier I was saying that, you know, some of the things that it might detect that it would classify as a human would be human legs. And in this case, I tried it with this image where, of course, her dress is obscuring her legs. And as a result, the classifier and the filters to detect legs in this case got confused, and it thought that this was actually an image of a horse. So there's always these kind of tweaking that you have to do, training, experimenting with your model, but this is how you'll end up building an image classifier. So with that, I'm going to wrap up. I know it's almost time for Josh to talk, but I can take a couple of questions. And hey, Josh.
Good morning.
I guess if there's no questions, then please, I'm on Twitter at @elmaroney, and feel free to ask any questions there, and I'll hand it over to Josh to take it away. Morning, Josh.
Good morning. I'm not sure if y'all can hear and see me yet. I think I might be in the show. So hey everyone, I wish I could see you all in person, and hopefully next year we can hang out at a conference or a meetup. But I'm glad to see you virtually. So that was a really great talk by Lawrence, and I'll follow up with some more background and a few more details in case they're helpful to you. And this is an intro to deep learning. It's a bit of a long talk, so we will get through as much of it as we can. And we will have a longer version of it posted to the TensorFlow YouTube channel in about 3 weeks, in case that's helpful to you. So here's a quick outline of what we'll cover. I'll start by pointing you to a few demos that I hope will be helpful to you. And these are actually written in Python, in JavaScript. And there's 2 that are really cool that you can build on top of, and 1 you can use if you're ever teaching machine learning yourself. And I hope that will be valuable. So let's just take a look at these really quick. There's roughly 2 ways you can use machine learning models. And the first is, as Lawrence just showed, you can write your own. And the second is you can use pre-trained models and build on top of them. And this is a pair of models that you can find on the TensorFlow blog. They're ready to go and they can run out of the box. One is doing face tracking, and you can see on the left that it's identifying key points in someone's face as they move. The second, of course, is doing hand tracking. These are both written in JavaScript, which means you can run them entirely in a browser without writing any code. And that means you can develop really valuable applications on top of them. For example, on the left, you can imagine maybe you have a user who's movement impaired, and perhaps they can't move below their neck. By moving their head around, they could easily control a mouse cursor. So there's a lot of low-hanging fruit like that, especially in the JavaScript world, although most of the time we write our models in Python. The second model I think you might really enjoy is called, or the demo that you might really enjoy is called the teachable machine. And the teachable machine, it's a way to train a very simple image classifier in the browser without writing any code at all. I highly recommend it. And if you're teaching yourself, this is a really great way to kick off the event, because all of the students or the developers in your group, they can train a model and see how it works in the browser before diving into code. So with that said, let's take a look at a bit of context, because deep learning, it's the area of machine learning that I'm most interested in, but it's also just a small set of the whole machine learning world. So roughly, we're looking at a diagram here with 4 circles. The outermost circle is AI, and AI is the most general area of, it's the most general term, artificial intelligence. And when you're doing AI, one sec. Yes, let me hit present so you can see the slides. I hope this is better. I won't be able to see comments from the organizers now, but that's okay. So when you're doing AI, that basically means you can pick a problem that people are good at, but machines are bad at, and try and solve it in any way you like. So a classic example of that would be programming a computer to play chess by searching the game space. Machine learning is the next circle, and examples of machine learning are things like decision trees or logistic regression or k-nearest neighbors. And if you're brand new to the machine learning world, this is the best place to start. And machine learning is basically a fancy word for programming with data. And to make that really concrete, the simplest example that I can think of is something like linear regression, where maybe you have a scatter plot and you're trying to find the best fit line. And maybe the equation for your line is something like y equals mx plus b, right? There are 2 parameters there, m for the slope and b for the intercept. And machine learning means starting with a random guess, like you saw from Lawrence, and then adjusting that guess over time. And that's what's happening inside model.fit. Then we get into representation learning, and this is where deep learning kicks in. The idea in a nutshell is that most problems in up until like 2012, basically, if you were doing machine learning, typically you had a small number of features. And this would mean you're working with something like structured data or tabular data, which is something you have in a CSV file or a spreadsheet. And you have a small number of features. For example, maybe you want to write a program to predict somebody's risk of heart disease. So your features could be the patient's weight, their height, their blood pressure, their age, things like that. A small number of features that you and I can understand as people that are easy to reason about. Now in deep learning, we have a very large number of features. For example, in horses versus humans, you saw that folks where you're working with images. And in an image, the features you have to work with are just the raw pixel values. And training something like a decision tree on pixel values doesn't make, it wouldn't be very sensible. Deep learning automatically learns good representations of features for you. And this is a cartoon diagram of a neural network that I want to pick apart very quickly for you. At the top, you see the input layer. And this is where each box here represents a pixel from an image that's being fed to the network. Every edge represents a weight. And these are all initialized randomly, and they're trained over time with gradient descent. Every circle represents a unit or a neuron. The very last layer in the network is the output layer. And that's where you get your classification that tells you if the image is a horse or a human or something else. And the intermediate layers, those are the ones that are automatically going to learn features. And the idea is this: the first layer is computing combinations of pixel values. And combinations of pixels gives you simple features like an edge. So the width of the layer is roughly telling you how many different types of edges that layer can learn to recognize. The second layer down in the network is learning combinations of edges. Combinations of edges could be something like simple shapes. And so the final layer is learning to classify the image in terms of shapes rather than in terms of raw pixels. And that's what the deep in deep learning is doing. The deep in deep learning means the neural network is learning a feature hierarchy automatically, so the last layer can classify your data in terms of the features that have been learned, rather than having to work with the raw pixels. And this is what makes it so valuable when you're working with images. And this applies, of course, to text too, and sound and any other type of data, but it's easier for us to see with images. This is an example from a technique called Deep Dream. And if you're interested, there's actually a work and research that shows you how to visualize some of the features that the network has learned to detect automatically. So for instance, on the far left, we're finding images that neurons in the early layers have learned to detect. And we see that there are different types of edges and patterns. And as we move to the right, we're visualizing neurons later in the network. And we'll see that they're learning to detect much richer features. The reason that we see things like these beautiful flowers and there's peacock feathers and some buildings, and it looks like somebody might be playing. I see a leg, I believe. The reason that we're seeing these features is that this is dependent on the data set that the network was trained on. And this particular data set had many pictures of flowers and stuff like that, which is why we're looking at them. I'm going to skip some slides to keep this short, but here I'd like to show you exactly as Lawrence was showing you that TensorFlow makes it very easy to define a lot of different types of models. And you'll find that although writing the code is hard, most of your time is going to go into studying the underlying concepts. And this is what we want. TensorFlow makes it easy for you to write the code. So this is a model for linear regression. And here we have a single layer with one output. And no activation function means that we're not going to change the output after it's produced. So this value could range, it's just a number that ranges between positive and negative infinity. But this is a model for linear regression. If you want a model for logistic regression, and that's a fancy way of saying we want a model that returns a number that's probability-like, so it ranges between 0 and 1, we can apply an activation function here called sigmoid, which will squash the value to be between 0 and 1. So now we have a model with one value between 0 and 1. Another thing you might want to do is classify something like an image. And in this case, we have 10 possible output values. And there's another activation function called softmax you might see a lot, which basically means to return a probability distribution. And what that means is every one of the 10 outputs is going to range between 0 and 1, and they'll all sum to 1. So we can interpret it as a probability. With one more line of code, you now have a neural network. And still, the way to read, anytime you see a neural network like this, the way to figure out what it does is to read the last layer. So the last layer tells us that it's producing 10 values in a probability-like distribution. And the layer above that is doing representation learning. So maybe that's finding some edges in the image to make it easier for the next layer to work with. And in the longer talk on the YouTube channel, you can learn about what ReLU is doing. If you'd like a deep neural network, again, you can do that with one more line of code. So now we have a deeper network that's doing more layers of representation learning. And there's an even deeper neural network with one more line of code. A really important part that I want to make is usually when you're learning machine learning, you spend a lot of time on code that looks like what I just showed you. And that's the part of this slide that says defining your model or designing your model. And the truth is this is the smallest part of your job, but it's also the hardest mathematically and technically. And it usually takes the longest to learn. But the most important skills in data science and machine learning are really problem framing, which means thinking about exactly what problem you're trying to solve and how will users use your solution and what could go wrong. And then machine learning is always data-driven. And so the most important thing of a successful machine learning experiment is a really rich and diverse training set that represents the data that your model is likely to be used on in the future. And then at Google, we spend lots of time on evaluating and testing our model. And another way that you can do really successful machine learning work without necessarily writing your code yourself is reusing existing models and applying them to new domains. And what I'm showing you here is, this is the homepage of JAMA, which is the Journal of the American Medical Association. And this screenshot is a little bit out of date, but what it's showing you is that the most cited paper in this medical journal from the last 3 years was this paper on predicting diabetic retinopathy. And this was work done by Lily Peng and her group. And they did an extraordinary job. And what's really special about it is they applied an existing computer vision model to the medical domain with a really thoughtful evaluation, really good testing, and really good training data. And so they didn't spend a lot of time writing the model itself, but they did spend a lot of time running their experiments. And you can do the same thing. It was an incredibly valuable contribution in applied work. There are many different families of neural networks. And because we have 10 minutes left, I actually want to go in, I want to skip a few slides forward, and I want to show you, I want to pick apart this diagram a little bit for you so you can see what's happening under the hood. Basically, there's two parts to using this neural network. The first is called the forward pass, and that's what happens when you do model.predict. So the forward pass means that an image flows through the network and the model produces an output. The second part is called the backward pass, and that's where we adjust all of the weights using gradient descent to optimize the model. Just so you know, the way we get the gradients is using an algorithm called backpropagation. Anyway, right now I want to look at just the forward pass. So I want to pick apart exactly what one of these neurons is and what's happening inside them. So let's take a look at just this little neuron here on the top left. So here we have a diagram of what's happening inside a neuron. And on the far left of the screen, you see these x's, x0, x1, and x2. And this is these are the input data that's fed to the network. So these could be the pixel values. Theta 0, theta 1, and theta 2 correspond, these are the edges that you saw in the larger diagram. And these are the learnable weights or trainable parameters. To compute an output, and it's shown graphically and with two different styles of math on the right, depending on which you like. But we multiply every input by the learnable weight, and we sum that all up. So we're taking a linear combination of the inputs and the weights. That produces a number. And earlier you saw that if we don't have an activation function like sigmoid, then we have a linear regression model. It's a number between positive and negative infinity. Or if you apply something like a sigmoid, then you can do logistic regression. You have a number between 0 and 1. So a single neuron is like a little, with sigmoid activation, is like a little binary classifier. It's also a binary classifier without it if you say that if the number is greater than 0, it's a horse, and if it's less than 0, it's a human. Anyway, here's another way of drawing exactly the same thing you had before. So on the left, we have an image, and here let's pretend that it just has 4 pixel values. And that's been unrolled or flattened into a vector, which you see here is x. So these have the same values that you had on the image. And doing the forward pass of a neuron or computing an output means multiplying every weight by the input, summing that all up and adding a bias, and that gives you a score. And on the top right of the screen, you see a little cartoon neural network that we're building up. And I ran out of space, so really this should have 4 inputs, but I drew it with 3 for space reasons. The point is, I want to show you how we grow to a dense layer. Now, if you look at the diagram on the top right, you'll see that it looks a little bit more like a neural network. And the only change is there's a second output. To make that happen in the math world, we still have one image, but now we have a second row of learnable weights. And so instead of doing the vector W times the vector X, now we're doing the matrix W times the vector X. So by adding one additional row of weights, we can still compute the output of this layer by doing W times X plus B. And this should give you some intuition to why GPUs are so popular in deep learning. Doing deep learning basically means multiplying a bunch of matrices together under the hood. And GPUs are extremely fast at doing that. They let us multiply matrices faster, which I just said is early. But anyway, that's sort of why GPUs have become so popular. On that matrix, and you see with a second row of weights, we get a second output. So now our little model is producing 2 scores, one for plane and one for car. Another really cool thing you can do, you'll see we have the same neural network on top, and really, actually that's a bug. I added a third layer of weights. So really we should have one more output. There's one output for every layer of weights, and you can see that here too. But what I wanted to show you is that now we have 2 images, and you see that we added another column with another image to our X. And the equation for this dense layer, or this layer of the neural network, is still W times X. But now we get 3 outputs, because we have 3 rows of weights for each image. So we can actually classify 2 images at once. And in the code that Lawrence was showing you with things like model.fit, This is called the batch size, which is a fancy way of saying how many images you classify at once. The default in Keras is actually 32. And again, that's another reason that matrices are so popular. So let's see how we go from that single dense layer to a neural network. And what we need to do is add a second layer. So what you just saw here on the bottom was W times X. That's the equation for one dense layer, followed by an activation function, which we don't have too much time to talk about now. But briefly, softmax just squashes the values that come out of that, so they range between 0 and 1. A neural network means following that up with another layer of weights. So it's W times X, followed by some nonlinearity or activation function, which can be usually sigmoid or ReLU, followed by another matrix multiply. And this is another way of showing that. So everything you just saw is the output of the first dense layer, and then we first apply an activation function, and then we multiply it by another matrix of weights. And there's many different activation functions. Just for brevity, you have things like sigmoid, which squash the value between 0 and 1, and you have things like ReLU, which sort of function as an on-off switch. Anyway, if we apply something like the activation function, and here I'm just showing you ReLU, and I know this is fast, I just want to show you that it modifies the output values of the layer. So these were the output values of the layer that you just saw. We're applying G, which is some activation function, and they adjust them a little bit. This becomes the input to the next layer. Basically, instead of having the next layer receive the pixels from the image, the X's in the next layer would be these values that you see here on the right. They're the output from the first layer. And if you repeat this pattern again and again and again, you'll see that a fully connected deep neural network, it's a matrix multiply followed by an activation function, followed by a matrix multiply, followed by an activation function, and so on and so forth. And what's really interesting about deep learning is, although it's the most powerful area of machine learning, it's by far the least intuitive. If you're like me, then your brain is built to understand things like decision trees and maybe k-nearest neighbors. It's hard for us to reason at exactly what's happening inside these neural networks. And that's because really we're doing gradient descent in this incredibly high dimensional space, but they're amazingly powerful. One really, really important thing I wanted to mention about deep learning is that your code can compile and it can still be wrong. And this is a tip that even though your model might report that it has very high accuracy, that doesn't mean that it's actually doing the thing that you think it's doing. And this is a little toy example. But basically, and there happens to be a horse here, somebody trained a classifier to detect horses versus dogs versus cats. And they used, there's a variety of techniques that you can use, things like activation maps or integrated gradients that can help explain the predictions of a neural network. So they can help you answer the question, why did your model classify this image the way it did? And here we've asked the model to explain, why did it think this image is a horse? And what it's doing is it's highlighting this spot on the ground. And that tells us there might be a bug in the model, because we can see that it's not really looking at the horse. It's looking at this spot. And yeah, so it's just a very important part of doing machine learning. And you can learn more about that probably in about 2 months on the TensorFlow YouTube channel. There are many educational resources. I know Lawrence has a really great book. I wanted to point you to a couple more that I also really like. And a good strategy is what I personally do. I usually get 2 different educational resources, and I often read the same chapter in both. And sometimes authors explain things in slightly different ways. It can help you get 2 views of the same problem. The book on the left is still being written. It's called Deep Learning with Python, and it's by the author of Keras, and it's a really, really great from the ground up explanation of how TensorFlow works and how to write neural networks and what the intuition is for them. In the middle, there's a wonderful book with a very long title called Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow. But if you're new to machine learning entirely, I think this is the best place to start. And it will cover classical ML, things like k-nearest neighbors and decision trees and logistic regression, and then walk you into neural networks later. The book on the right is totally free. It's called the Deep Learning Book, and you can get it online. And it's an academic textbook. So there's no code in there, there's just math. But it's a great piece of supplementary reading if you're interested in some of the mathematical details behind the higher level concepts. So thanks very much. I know this was a super quick talk. I can't wait to see you in person, hopefully in 2022. I'll be out there as soon as it's safe to do so, and I hope you're all doing well.
Thank you very much, Josh. So Joe, that was a very quick introduction. I have one question before I even jump into the questions others may have, which is usually when you break down the steps of machine learning or the steps of deep learning and talk about model building being just 5%, why is it very difficult for people who are getting new to machine learning to either accept that or understand that all the mathematics could just be just 5% of solving an entire machine learning problem? And how do you get that message across?
Yeah, so that's an excellent question. So I think the reason that it's hard to accept that it's such a small percentage of the machine learning workflow overall is that it's very hard. And the truth is, it takes about a year to learn to do machine learning from the mathematical side. Typically, there's at least like 2 classes you would take, and it has some like fancy prerequisites like linear algebra and calculus and stuff like that. But because the libraries that we have today are so high level, and because you can define a neural network in just a few lines of code, it means that in 2021, in practice, this is the easiest part of the whole thing. Another reason that's true is that machine learning is data-driven, and there's an infinite number of designs you can have for your neural network, but there's a very large number of them that will work well enough. And the way to improve your model is usually not messing with the model itself, but it's to get more data or to spend more time testing to make sure that your system works really well in practice. Another thing I can tell you partially as a joke, oftentimes a lot of new engineers, when they get their first machine learning job, they're like, yes, like I'm going to spend all this time writing this really cool code for the neural networks. And then what happens is they actually spend lots of time just focusing on the data set. So.
Okay, so we have a question. And if you want to take a shot at it, can anyone explain how TensorFlow supports OCR? That's a wide question.
Yes, so happy to. So great question. So OCR, or optical character recognition, is a very important area of machine learning. And it basically means reading text. There's 2 ways to work on this problem. We have a good example for OCR on Keras.io. So Keras is the high-level library that you saw today. And if you check out the code examples, and I will just type a link into chat so you'll have it. Actually, or maybe if you could please share this with the chat. You should be able to find one for OCR. But this is a bit of a special case because OCR is a very generic problem because there's only so many different letters, of course. And what this means is that if you train a huge model on an enormous data set, that's probably better than training your own model from scratch. And so OCR is like the only problem that I would recommend that you use a cloud service for. And there's many different paid cloud services. Google has one. I'm sure other large companies do as well with Google Cloud Platform, where you can upload an image, pay by penny, and they'll run OCR for you. But if you prefer, you can train your own model with Keras.io.
That's awesome. Josh, I really want to thank you for joining us. And like I said, and like you said, you have another question from Robinson. Let's take that before I sign you out. Can TensorFlow LRO images format? And what are the options to convert to TIFF?
Yeah, so good question. So basically, as you saw on the slides, once you start working with the images in memory, the images, it's basically just a vector or a matrix. And TensorFlow supports a variety of image formats. And there's a whole library called tf.image that can help you read images in different formats. So yes, it does. But there's almost 2 different steps. You know, the first step is reading the image, and after you have it read, when you're feeding it into your network, at that point, it's just a matrix. So yes, it does support those different formats. Check out tf.image.
Awesome. Thanks, Josh. Really glad to have you. And we're going to hold you to your promise of having you over in the region as soon as we can all fly around the world once again. Thank you very much, and have a good rest of your day.
Thank you very much, and you as well.
Okay, so we're welcoming Gus, Luis Gustavo Martins, Welcome, Gus.
Yes, I can see me now. Hi, everyone.
Hi, welcome. We can hear you.
Nice. That's very good. Hope everyone's having a great day.
Yes, we are. Please take it away.
Nice. Hi, everyone. My name is Gus. I'm from the developer advocate team from TensorFlow, just as Lawrence and Josh. I'm trying to keep up the pace, but it's very hard to follow them because they're great, but I'll try my best here. So today I'd like to talk to you about on-device machine learning, what it is, when would you use that, and some examples in the wild, and what can you do with it, right? So let's go right now. Oh, if you want to follow me on Twitter, it's at Gustema. I usually share knowledge about machine learning, Python, and TensorFlow, of course. So if you have any questions, just follow me and ask them. I'll try to answer. Let's try to understand what's this edge ML explosion. So the thing is, first we start with machine learning, and it's cool, and you can solve a bunch of very good, nice problems like vision, text, and others. But then that was so good that people thought maybe we should use that on other places outside of our servers. And how can we do that? And when people found out that you could run a model on a device, that changed a lot of things, right? Because then you have a phone, and everyone has a phone, and maybe you can use the machine learning model on pictures from your phone. So that's a huge thing that you can do now. It completely changes. And then what happened is that the phones start to have more and more hardware to support this journey. So now they have specific chips to help with machine learning. They have more memory, they have more processor power, they have more space. So this is making easier to deploy a machine learning model on the on device. And there are some other parts that we should pay attention. When we want to run machine learning on device, we are worried about some other things that the device can do. One of them is a lower latency. So for example, if you want to get some insights from an image, the old way or the regular way, right? It would be like you take a picture, get this image, upload to your cloud server, run the machine learning, no matter how fast it is, and then you send back the results. No matter how fast your server is, it will still take the round trip to take the image there and get the result. And this is definitely this will definitely take longer than one frame in a video, for example. So if you want to do this with lower latency, like just look at an image and a result, or apply that for every frame in an image in a video, then you cannot use the cloud, right? You have to use something closer to you, which would be your own phone. So if you want to do that, that you can only do that on the edge side, as we say, right? The other thing is sometimes you want your model to don't rely on network connectivity at all. Or maybe you are in a region that the network connectivity is very bad. You're far from any antenna, any Wi-Fi, anything. So you want for your prediction models to keep working, keep giving you predictions. So for example, if you have a camera that does some fancy processing during taking a picture, and then you go for a hike in a mountain or in a forest somewhere beautiful, but then you need the connectivity to take a picture, right? To help you with taking this picture, and then you have a problem, right? When we start to run on-device machine learning, we are trying to also hide that, to run everything offline, everything completely local. When you do everything completely local, you can preserve privacy of your user. So you don't need to upload your user's picture, your user's data to anywhere. You can just run everything locally. So in terms of privacy, this is way better. So you can guarantee your user, look, I'm just working on your image locally, giving you insights. Nothing is going out of your phone. So this is another advantage of running things on device. And doing that, you are creating a new generation of possible products, some things that weren't even possible in the past. Now you can do them just because of this power, right? So let's see some examples. Here we have YouTube. YouTube has one feature, let's say, that allows you to try makeup right in the app. So there's a YouTuber presenting, oh, there's this makeup here. If you want to try that, those are the colors, and then you can just use right locally. This is the kind of thing that's you cannot do that with the cloud, right? Because for each frame of the image, if you upload to the cloud and come back results, it's not real time anymore, so it gets a little bit clunky. So this enable this kind of feature, and of course Google Translate. I'm pretty sure most of you have seen that. So what Google Translate does is it uses OCR, as you can see on the little video there. It's using OCR, extracting the text, and then translating to the language that you selected. In this case, it's English. So the thing is, it's more than one model here. So there is the OCR model, there is the translate part of the model, and use both of them to give you a result. This is something that's was completely unthinkable in the past, right? Because everything is running completely on device locally. That's why it's so fast. How do we do this? And then the next question I have is, okay, I agree with you, Gus. This looks like a good idea, and you should. But how do we do that? How do we get there? And this is where we have TensorFlow Lite. So TensorFlow Lite is the framework to deploying machine learning models on mobile devices and embedded systems. It's not only Android. We are going to see there are a bunch of devices that we can use here. And this is the same framework from TensorFlow, but it's a version that's created to run on device. And this has some, there's some points you have to pay attention that takes into account why this is special, why it's different. So we are going to go into all those details. Among the devices that the TensorFlow Lite platform supports, we have, of course, Android and iOS smartphones. We have Linux-based devices like Raspberry Pi and other dev boards that we're going to see in a little bit. And we also can run that on microcontrollers, like Arduinos. And let's see in more details how it works on the phones. Today, there's thousands of products already that are running machine learning on device. So of course the Google ones, as we all know, YouTube Assistant makes a lot of sense, and then we have other developers that are also using machine learning for multiple use cases. For example, some use cases might be related to here when we are on a video conference and you want to blur the background, right? Here I'm not blurring my background, but some video conference apps allow that. This blurring is running machine learning on device locally. And for example, if there was captions, closed caption on what I'm saying, also machine learning running closed captions locally. We have Gboard there, for example. Gboard tries to find, if you swipe on it, it knows which words, and these statistics of the words and how to get there, they are all based on machine learning and running completely on device, right? So your data doesn't go to any cloud, it's just local for you. Aside from that, TensorFlow Lite can help you in all kinds of tasks in machine learning, not only image, because we talk a lot about image, I guess because that's the simplest example we can come up with. But it also works for text classification, prediction, for speech detection, but we've talked about the closed caption, right? That's a speech recognition, image with a lot of kinds of tasks into image, like object detection, image segmentation, facial modeling, and so on and so forth. Of course, audio, if you want to track audios, and also if you want to generate content, if you want to generate parts of a video, generate text. And so TensorFlow Lite can help you in all of those tasks. And if you need some examples of what's available already, we have this web page here, which is the main examples page for TensorFlow Lite models. What you find there is the problem. Like, for example, there's image classification. There is a source code for samples for Android, for iOS, sometimes for Raspberry Pi too. It's explaining how the source code works, explaining how the model works, and it gives you everything so you can learn from there easily, right? So this link is kind of important if you want to play more with TensorFlow Lite, and you should. So this is one thing. The other library that can help you is MLKit. MLKit is it's a library over TensorFlow Lite to help you apply machine learning on on device. It has some already pre-created use cases that will help you, and with these use cases you can already easily, you don't need to worry too much about models or TF-Lite or anything. You just use the API. That will make your life easier, but it's all based on what TF-Lite is doing already. And if, for example, your use case that you want to implement is not there on MLKit, you will need to fall back to TF-Lite as usual. Does it make sense? Is it going to say anything? Okay, no, someone connected. Let's see how it works with Linux-based devices like Raspberry Pis. We have our friends from Ecovacs, and they have these vacuum cleaner, right? These robot cleaners, and they are using machine learning on these devices to detect things and avoid hitting obstacles while cleaning the room. And this is a very nice example, right? We would expect this kind of robots to see if there's anything in front of them and take another direction, change, don't hit anything, right? So this is a very nice use case. Aside from that, we also have something called Coral, which is a streamlined version of what TensorFlow Lite can do. And these models, they run on a chipset called Edge TPU. And these are, as you can see, there's a coin there. So chips are super, super small. And TF-Lite models run on this chip super fast. And this is something that can enable some way more use cases than only on the phone, right? Here we have some examples where you can find these Coral products. For example, we have a dev board if you want to create something, create a product. And the cool one I like is that USB accelerator, which is like a pen drive, but you have an Edge TPU inside of it, so you can connect on the USB port of your dev board or any Raspberry Pi device, and you can run your model on this, and it will be super fast. Even if your Raspberry Pi, rest of it, it's just not as advanced, this will help you run models like you can do frame by frame on a video, for example. That's very good. There's some other hardware. I'm not going to go into too much detail on them right now. Let's talk a little bit about microcontrollers and what they are. So first of all, let's try to understand what's a microcontroller. Microcontroller is kind of a computer in a single chip. So if you think about that, that's like the smallest piece of computer that you can have, and they are available they are already deployed in multiple things. For example, on a refrigerator, microwave, smoke detector, toys, multiple sensors. So what TensorFlow Lite enables you is to run machine learning on these devices. And some of these chips are absurdly fast for specific kinds of mathematical operations. And when they do that, they can run models absurdly fast if you know how to do that. TensorFlow Lite give you access to that, even though they have, of course, not as much memory or processing power as a phone, and they use way less energy, less power. So they have a lot of advantages here. And even if you think you're not using any DSP already, you are kind of are, because when we do hot word detection on Pixel devices or other phones, what they do is they are running this model for keyword detection on the DSP of your phone. Your phone has this kind of chips too. And because they use so not that much power, they are very good on conserving energy. Keeping a model running on it all the time doesn't spend too much battery of your phone. So that's the way we can do hot word detection on a phone and just say keyword and the phone wakes up. So it's because some specific chips are monitoring the audio of, it's not non-stop, there's some algorithms there, but they can, he said okay Google. I don't like saying that because then all my phones, they wake up. So if you say okay Google, they will, the assistant will come up, because the DSP is waiting for, as I said, the DSP is waiting for this kind of instructions to, hey, someone is calling here, and then it wakes up the phone and gives control to the proper processor to continue from there. So the model that does that is way smaller. It's not like a speech detection one. It's a keyword detection, which is way smaller, much simpler. So this is how these kind of things would work. So if you want to play with that, right now there's an official Arduino library, and there is a 5 minutes speech detection tutorial that you can follow. There's a link over there. There's thousands of possibilities here, and running machine learning on super small devices, that's some very cool things. I've talked to you a lot about how to run these modules on the device. And then you're thinking, yeah, but what's the drawback here? If people say, oh, you need a lot of machines and processors and memory to do all of this, how can it run on the phone? Where there's something missing here. And the point that's very important, when we aim to run models on edge devices, we call edge devices the one around, right? Mobile and Raspberry Pis and all those that I mentioned, is because you have to work on this model to take into account the hardware constraints that you have to face. So let's take a look on that. First of all, optimizing your model is very, very important. The same model that runs on a server might not work at all on a phone. And we are going to see some examples here. Because first of all, you have limited compute power. No matter how amazing is your new phone, it's still not as fast as a server, right? That makes a lot of sense. You don't have that much memory. Same thing. No matter how advanced it is, not the same as a server. And the other constraint that phones and edge devices have is they have a battery that they have to be conservative about it. They cannot, oh, let me just keep running this nonstop. The battery run out of power, and then the user cannot use the phone anymore. So this is a problem. You have to pay attention to that. And there's the app size. If I give you 1 gigabyte model to run on a phone, and the 1 gigabyte model to just run your phone, the user might look and say, no, I don't want this app anymore. It's like too big. Like this is too much. So app size is also very important. So how can we address these constraints with our models? So first of all, there is some things we can try to do here. Let's go one by one. First of all, when we deploy a model on the edge device on a phone, there are you should use one model that's optimized for a model for mobile architecture. So you don't use a model that's optimized for a server. You use a model that's optimized for a phone, for a Coral device, for a microcontroller. Those models, they take a lot into account already to make it fit inside like a phone. The other thing is you can, after you have your architecture that's compatible with a phone, you can apply quantization to it. I'm going to come back to that. What's quantization? And you can apply also something called pruning. I'm coming back to that also. And the last one is leverage hardware accelerator. And that's using the special hardware on your phone to help you do the inference in real time. Let's go to optimize architecture. So here I have two examples. On the left, we have Inception V4, which is a state-of-the-art model for image classification. This is a big model that runs on servers. It's amazing and all. We have also the MobileNet V3, which is kind of super new, and it's, as the name says, focused to run on on-device machine learning. And here we start to see some amazing things. First of all, the top one accuracy for Inception V4 is 80%, and for MobileNet V3, 75%. So you're talking here about almost 6% difference. So your mobile model is 6% worse than the top model on servers. But let's take a look here. 80% is amazing. So if the computer looks into an image, it has 80% chance of telling you correctly what's in the image. When you go to the phone, it's 75%, which is still great, super good, right? When we talk about top 5 accuracy, is I will return you 5 things I think are on the image. And of course, this is the accuracy here is higher, right? Because I have 5 options to find out what it is. And for on device, you can see that's 92. It's still great, right? If you're, for example, if you have a app that the user looks into a picture and you want to give tags, like this is a picture of pets or has a dog, and then you can help the user categorize their pictures, right? Returning a top 5 accuracy, all 5, and then the user choose which category he wants, that's huge, right? That's very good UI. That's very good use case. And with 92%, it's still super great. And now we can see the super advantage here. When we run Inception V4 on TF Lite, it takes 320 milliseconds. That's like eternity in phone's perspective. But when you run that, when we run the MobileNet V3 on the same framework, it takes 8 milliseconds. So this is 37 times faster. And the 8 milliseconds, if you think about a video or the rendering pipeline of phones, they render a frame every 16 milliseconds. So if you can do inference every 8 milliseconds, you can run inference for every frame on a video, right? So this gives, you can run on a video, inference on a video and do way deeper analysis there. While the Inception V4 take a couple of minutes, not minutes, but it will take a long time to finish one execution, right? So this is a huge difference, and you're having only 6% difference in accuracy. So that's good. And the other super advantage is the Inception V4 is 170 megabytes of size, while MobileNet V3 is 22 megabytes. It's almost 8 times smaller. So look the difference here. This is big, right? And this is how we use a proper model architecture to help. Here we have a graph with a lot of state-of-the-art models, and you can see that, of course, the smaller the model, it has less accuracy. There's no magic there. But you can get to a compromise that's good for you, that has a very good accuracy with not that big of a model. So this is just to highlight that. Let's talk a little bit about quantization. So if you think about what a model is basically a very long equation full of floating numbers. That's basically what it is. And then when you load this equation with TensorFlow Lite, what it will do is it will get the input, apply to that equation, and get a result. The thing here is this, for every a times x plus b times x1 plus c times x2 and so on and so forth, all these a, b, and c, they're float numbers. And float numbers take a lot of space. And one thing that researchers found out is you can decrease the float32 to an int 8-bit size number, and you won't lose that much accuracy at all. So this I forgot the English word for that. Sorry. Completely forgot. So taking this decrease in accuracy, it's super valuable, and this is something that makes models much smaller, and you don't lose too much accuracy. Let's take that. Here we have a good example. We have 3 examples of models, and we have the accuracy of them. And then we have the float version, the float32 that I just mentioned. And we have on the side, if you do the quantization to integers, you can see that you lose like 1.5% in the first one, but the other is like less than 1%. The last one is not even 1%. So you can see that you can make your model way smaller and you still have a very good accuracy. So quantization is your friend, and it will help you with deploying models. Also pruning. If you think, I guess Lawrence and Josh mentioned, like you're creating a network, right? Like a graph. What pruning does, it goes over some of the weights of your model, and if they are too close to 0, they just make them 0, and then they remove them. Of course, you are removing information from your model. It will definitely get less accuracy, but the how much less we are going to see in a little bit. But the idea is you make your model smaller. When you make your model smaller, it will run faster, so because it will load faster, and it has less, let's say, items in that very long equation I mentioned. You're removing some of those because they are very close to 0. They might not affect. So pruning is very important. And as I said, smaller models, it's easier to compress them. They have less complexity inside of them, and they since they use less operations, they of course run faster. And here we have an example, right? So we got a model. I don't know if the name of the model is MobileNet. So we got MobileNet accuracy, which is and so the accuracy is the y-axis, and the how much pruning we are going to do is on the x-axis, right? So here for 50%, so we are cutting 50% of the variables, let's say, from your equation. You've got negligible amount of accuracy drop. You can see that's very, there's not much at all, like it's less than 1%. And if you start to cut more and more of these nodes, your accuracy starts to drop and drop until up to a point where it drops too much, right? So pruning is an amazing thing to help you make your model smaller and faster. Now let's take a look on all the results at the same time. First of all, if you run your model on device only on the CPU, this is for the MobileNet V1, right? It's a model that the architecture is already focused on device, focused for running on device. It will take 37 milliseconds. 37, not great. You cannot run every frame. If you quantize the model and it still runs on the CPU, remember, CPU is not specialized on running machine learning models, right? It will drop from 37 to 13 milliseconds, which is, it can run every frame now. So the quantized version of the same model, it's already almost 3 times faster. If you run the same model on a GPU, you are almost double the performance, right? You go to 7 milliseconds. And the thing is, you just, for TensorFlow Lite perspective, it's one line of code. If the model is compatible with GPU, which it probably is, you just say, okay, use GPU. That's it. And then you got 7 milliseconds. If your phone or your microcontroller has an edge GPU, it goes from 7 to 3.2 milliseconds, which is super fast. This is absurdly fast. And if you have a Hexagon DSP, remember I mentioned DSPs? So Hexagon DSP, some phones have that. And you can, same thing as GPU, enable. Just say, run on DSP. You go to 2.8 milliseconds to run an image classification model on your device. This is super fast. And this is based on multiple optimizations that comes way after you train your model, right? So you get your data, train your model, blah, 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 blah. From the moment you convert to run on the phone, this is when you start to look into this part of the playing around, right? So there's kind of some work to do here, but you can see that you can do great stuff. I'm not going to go into too much more details. There's a lot to talk about when we talk about TensorFlow Lite, but I just want to give you an introduction of what's on-device machine learning. I hope it was useful and that you got some ideas and want to play around with that. Follow our tutorials, our guides, explains everything. We are always working to make this easier for all the developers. So yes, follow up. There's the documentation there, tensorflow.org/lite. And again, thank you very much for your time. I hope you enjoyed. If you want to follow me, I'm on Twitter. Yes.
Amazing. Thank you so much, Gus. It's been a long day for many of us. I know it's quite early for you. But we have a few questions, which we're going to pop on the screen. I have some, but I'm going to put Nuruddin's question. How does pruning differ from dropouts?
Dropout happens during training. So so if you have a layer that's a dropout, you're doing kind of a pruning during training. So your model learns how to adapt that during training. Pruning is after. It's when you have your model already, and then you look into the weights and say, oh, these weights are too close to 0, I'm removing them. So it's on 2 different stages of your model's life, let's say.
Absolutely. So this is very important for our region. There's a lot of work going on with access and devices, trying to find the $30 price point for a mobile device, for a smartphone in Sub-Saharan Africa. What are the hopes, or what are the opportunities, or what are your views of the $30 smartphone being able to run TensorFlow Lite and do many of these on-device machine learning tasks?
Of course, there's a challenge. You're not going to be able to do the same thing as a Galaxy S. I don't know, their top phone. You're not going to do the same super real time on a very large image. But if you're working on a smaller image to do some, for example, there is the detecting disease on plants, right? This is a very common use case. You don't need a high resolution image to do that. Of course, with a higher resolution might be better, but you're not going to do like, I want 99% accuracy. No. You want to take a look and understand how things are going. And some models you don't run on real time. You run on the background. So you are processing like a text, extracting some entities from there, or you're understanding audio. So this is completely viable to run on devices that are cheaper, let's say, right? With lower hardware power. But you can also use the Coral devices I mentioned, or the Raspberry Pi. They're cheap. They're cheaper. They're not cheap. They're cheaper. And depending on what you're trying to do, if you want to monitor, I don't know, your crops, you put some of those devices that can cost maybe $1 a device. Of course, I know it's money. It's not free, but it's way cheaper than a phone. And then you can still run your model and get some readings from your crops, from, I don't know, forest, from other things that from your car. If you want to, for example, people can run these microcontrollers on your car and detect when it's going to break. So it can monitor your engine, say, oh, your engine is not going well, maybe you should do something. You put a microcontroller there to try that. So there's a lot of opportunities here.
Yeah, and then my final question just has to do with computer vision versus things like natural language processing, especially voice. A lot of the people in this region probably don't speak English as a first language. So things around translation and understanding voice commands is also going to be very important. Is it more difficult? Because I've seen a lot of your benchmarks have to do with vision and stuff like that. Is it more difficult to do computer vision, or is it much more difficult to do things like natural language processing and have this happen on the device?
So they have two different problems here. The problem with the vision models are easier to understand. So that's why we explain a lot visual problems, because they're easier to understand, and the models that we can explain, they are easier to understand also, right? And there's a lot of data. When you go back to text, there is two problems with text. First, understanding text is harder from machine learning perspective. It's more advanced, so you need to understand more machine learning. And as you said, there's the language problem, right? For example, I speak Portuguese. My main language is Portuguese. If I want to do a model for Portuguese, I have to find out a database of Portuguese speakers, which is not as easy as an English one. So there is the problem that the model is more complex, and that finding a proper data set is also not as straightforward. And the same for audio. Audio has a lot of data sets, but maybe not for the language we want, right? So this is, there is pros and cons as easier and harder on both of them.
Awesome. I really want to thank you very much for joining us. Like I said, it's been a long day, and we expect a lot of people are going to watch this like as a recording. So if there are any questions, we'll come back to you through your Twitter handle, or if anything gets funneled to my email, I'll be reaching out to you directly to provide answers directly to people.
Of course.
Thank you very much, and we hope when the world returns to another normal, you would make the journey to come towards Africa, Nigeria, Mozambique, Angola. We've got Portuguese-speaking countries here as well.
Yes.
So we're looking forward to hosting you on the continent 2022 or 2023.
Let's hope so, my friend. Let's hope so. We can see each other in the future.
All right. Bye for now.
See you later.
Bye. Okay. I think we've had 4 good hours of machine learning sessions. We're waiting in for our final speaker. So we're just going to hold on a little bit and see if he's in here. We may have to end briefly, but we'll take a short break. And after this, just want to let you know that these videos are going to be available live, or are going to be available recorded on the YouTube channel. So the same link you used to join will be made available for you to join, for you to watch these videos after the broadcast is over. So thank you very much, everyone. And we'll hold on a little bit before we end the broadcast. See if our last speaker will be able to join, or we'll be having internet connection problems.